Hello everyone, how are you all doing? Hope I'm audible, guys. Are you guys able to hear me? Thank you very much. Let me share my screen. So before that, what did we discuss yesterday? We decided that we will spend some time on, you know, the projects itself, okay? Isn't it? Essentially, so what is pending from a recurrent neural network is this, is we will, maybe we'll just do a recap of LSTM very quickly, and then we'll see a, we'll see one more style called as Groove network. Okay, and then we might discuss a little bit on attention, but that's about it from the recurrent neural networks lesson point of view. Okay. And so what we discussed yesterday was that some sort of, let's discuss projects a bit, okay? And some of you have reached out yesterday. We were trying to open one of your labs, right? And due to time paucity, we couldn't. So is this the right time to discuss projects? Shall we do something about it? Okay. You, I can't share. So Suchita, I did not share a project file yesterday. Did I share a project file in the community? I just uploaded our explainer, isn't it? I think I just what did I? Sorry, just let me just go to the community link once, guys. I think that will be easier. I did not send any project file. Okay, project is there in your LMS. Please understand that. And if you are talking about this link, this is the link from the news aggregator dataset. Okay, so this is a CSV file from the stock price. We remember some of you were not able to get the price.csv. If you still can't access this drive, what I'll do is, this is my drive. Okay, it's not open. So what I'll do is, like, I've just opened it for this class. Okay. But you should be able to, can you click and just let me know whether you can access it? This is a zip file, okay? You can just download the zip file and you have to extract it and upload to your project lab, okay? So that is what you have to do. Let me know if you still can't access it, okay? Suchita, is this what you are referring to? This link, right? I am sharing my screen, right? I am sharing my screen, yes. So please confirm if this is the link that you are talking about. Okay, I think she'll come back. I mean, fine. From an assessment standpoint, okay, one of our learners were talking about house loan data analysis, right? Um, do you want to start with that, or how do you want to start with that? Do you have any obvious questions that we want to discuss? Maybe we can discuss that and then start going to other lesson plan. Is it? Let's do that. Anyone wants to start discussing that? If you have any specific question on any of the projects, let's deal with it now so that you will have some sort of time to actually talk about it. Okay? Any one of you. The floor is open, folks. I think what we'll do is, like, we'll focus for 10-15 minutes. Okay, if it extends, it's fine, not a problem. But maybe if you don't have too many questions, we might cut it short. But let me know if you want to discuss the project details and if you have actually gone through the projects or not. Have you by any chance downloaded this dataset file? Let me just open the practice lab also, okay? No, you can see that, right? I'm sharing my screen. House loan data analysis. It has a link for into our Dropbox, right? Can you see this project? Are we on the same page? Can we just all go to your assessment tab in LMS and open this project called as house loan data analysis? Okay, right? most of you have confirmed that this is the same project that you see. Okay, so you should see this link. Okay, this is a Dropbox. This is a Dropbox. This is the data set. Okay, this is actually the data set. So you should be able to download it. Nothing else. Yeah. And you have to recreate the whole of the code is something that is come from you, right? Okay. Awesome. Do you want, so have you guys started? If you haven't started, I think it's about time that you should start the project. And yeah, I think we have, Uttam, just can you share your doubts that you had yesterday? Maybe you can just highlight the doubts. We've communicated as well, right, yesterday? Can you please put your doubts here so that all of us can actually, understand that as well? Please. Please put your doubts here so that we can actually understand it. Okay. So let me try to download this. This is house loan data analysis. Okay. Okay. So I'm just downloading. The file is about 40 MB. Okay. So it's fine. I think let's let it download. Loan do I already have one. Okay. So guys, this is will be, if you have any questions, please put in the chat or anything related to projects. Okay, it's now 8:06 p.m. India time. My watch 8:07. So we'll go till 8:20. Okay, till that time we can discuss projects, I suppose. So let me just okay. So let me create a folder. Okay, projects. I just wanted to see whether we have this CSV file upload. Okay, this is 158 MB file. Okay, loan data. Let me rename it. Okay, and okay. So let me. The file is still getting uploaded, I guess. So this is house underscore loan. So do we not have any questions? Then shall we start the session, guys? Do you want us to start the session then? Oh, you're asking? Okay, okay. No worries. Take your time. Please take your time. Okay. Please take your time. No worries. No worries. No. No, no. We will not. We will not. Yeah, yeah. Please. IPYNB. That's what I did, right? IPYNB file. What did I do? File. Yeah. So IPYNB. Did I not do this? New. Okay. So the question is that you're having doubts related to the null value imputation. Before filling the null value, you've identified that there are outliers here and treated them. So you are asking me, is your approach is right or not for this loan data set? Okay. So let's do one thing. Yeah. I have shared one file. So that is going to be difficult. So let's do one thing. That is going to be difficult. What we'll do is like, let me, so you shared a link, right, yesterday on the Colab. Can we open that itself directly? I wanted to see that. Can you share that Colab link one more time? It's your own personal Colab, right? I can't open the file, right? Yeah, please open that Colab. Just send me that link so that I can open that file in Colab. Okay, you said that you have a watcher. Send me something. Let me just grab it. Okay, 1 second. Just 1 second. Just 1 second. Okay, got it. Okay, just 1 second. Save to downloads folder. Okay. So now what I'll do is like I'll upload this. So ideally we should not share this code like this. Okay, we should not share the code like this. But for this, let's go with it. Ideally we should not share the code like this. Okay. It's okay if you just share the Colab file. It's your code, remember that. So this is the file that you have shared. So Okay, let me see. So this is loan.csv. Okay, we are talking about 305751 loan underscore data.csv. Okay, I've opened it. Can all of you see? So what's your question is that? The question is that I am having doubts related to null value imputation. Before filling the null value, your cell number 28. Okay, let's go to cell number 28. Okay, so let me just understand. So we are missing values of, so this is good. Okay, good EDA. You have gone through methodically. Okay, some new columns are missing. That's good. So in this cell number 28, you are trying to show that this is his code. Okay, so so this is Shobha. This is his code. So he's asking a question. This is not from the course. Okay, this is his code. So he has a very specific question. We will quickly answer that. And if you have any question, okay, please raise it. I would highly encourage you to work on your code. Okay. So I'm having doubts related to null value imputation. Before filling the null value, I identified the outlier here and treated them. Okay. So this is the question in the column that you have is amount annuity. Okay. Can you allow to Asha? Is it possible for Uttam to speak? Can you give him the mic access, please? Asha? Just let me ping Asha once. Just let me check whether I can do it or not. Oh, I think I can do it. Sorry, 1 second. Just 1 second, okay? Okay, yeah, please speak.
Hi, sir. Hi, everyone. Good evening. Am I audible to you, sir?
Please go ahead.
Yeah. So, sir, you can see in the cell number 20, there is a one feature which I plotted, right? And there are so many outliers, right? Lots of extreme values are here, right? Then, sir, move to the 40 to 44.
So let's answer this question. Should you treat this outlier?
Yeah, I have treated, but
How have you treated the outlier?
Sir, I have treated outliers by Q3 plus 1.5 plus IQR, right?
But
With
you should not. But you
all
change
the
the data
values,
itself, is it?
yeah, all the values, sir, which are extreme values, right? I changed with like maximum with the like upper quartile.
Oh, understood. So the thing is that we should not change the values like this, okay?
Yeah.
It's okay. Neural networks, all objective is that it is not a linear function. It's a parametric function. It will actually create the curve accordingly. You don't have just one or two outliers, you have bunch of it, okay? If you have to call it as an outlier at all.
Yeah, so as sir, as you
Right?
can see, like cell number 44. So I changed, like I use like np.where method, and as I'm doing like in machine learning, I did the same, right?
Yeah. So point what I'm trying to say
So
is that
what I can do, sir, here, like suppose if I would
you
like to,
question answer to the question is that if you have an outlier, you should not treat the outliers like this anymore, okay?
okay,
The reason is that it's okay. They must see this is not so just given taking this particular amount underscore annuity sees that it is quite a lot of data. Okay,
yeah,
not just one or two we are talking about, right? So you're not talking. I'm not sure about the quantum, but what I'm
yeah,
trying to say is that
3.5 times
neural network is not a linear model. So it is okay. It will fit on its own. Okay.
Okay, so we can keep the outlier, sir.
Please keep it. Yes, you have to, or else there is the idea of non-linearity is broken, right?
Yeah. So, sir, suppose if we are keeping outlier, then suppose if we are going to impute for the missing value, then like mean or median are going to be mean or median are going to be high, right? So, which value I prefer, like median?
That is so. That is up to you. Only thing is that what is this amount annuity is about? Let me just what do you mean by this particular column? Any idea? What is this amount annuity means? Amount annuity. This is home.
Actually, sir,
Annuity
data
amount
dictionary.
yearly, is it?
Yeah, data dictionary is not there, so
The data dictionary that we have to see, right? So this decision is a very data science decision, okay?
yeah.
That whether mean is correct or mode is correct. I would say that from your point of view, go with mean, okay? If you are not sure about and if you don't have any data dictionary, go with mean.
Hmm.
Do not change the outlier values. Keep it as it is. And if you are worried about, if you are still worried about that, no, my mean is real, like gonna be really stretched,
Yeah, yeah.
it's
Like
fine.
mean is
It's
so
okay.
far away from the median, sir, here.
It's okay. It's okay. I think it's okay. Or what you can do is like, or what you can do is like,
Hmm.
the way you have computed in line number 40, 42, right? You have
Yeah.
fixed the outlier, get the mean of that and impute it. But in the data set that you're gonna send it to neural network, keep things as it is. For
Okay.
the outlier values, to compute the mean, adjust your outlier. Once the mean is computed, right? How many such data that we have missing values are we talking about?
Yeah, so you can check it, sir, around like here is actually I
Is
think
it is it a lot? Is it like 50%, 60%? No,
no,
right?
not 50%
Not
exactly,
okay.
sir.
Then it is fine. Then it is
Around
fine.
like 500,
Then
600 out of 3.5 lakhs required, sir.
then it is fine. Then it is fine.
So
Then
we can impute with the mean, right?
so you
And
know,
no need to treat the
yes,
outlier.
yes, yeah, yeah, please. So what I'm saying is that if since you do not have data dictionary, we are doing it right. Since you do not have data dictionary, go with mean. If you are still worried, only for the mean you can treat the outlier, get the mean, but do not change that particular column. The whole purpose of this thing is itself is that, right? Okay. I think
Okay.
we have one more caller who wants to speak. Uttam, is it fine? Does this answer your question, Uttam?
Uh,
Yeah?
Sorry, come again, sir.
Does it answer your question?
Yeah, sir,
Okay.
I have few more questions, sir.
Okay, please go ahead.
This is sir second question. You go for the cell number 71?
Okay, cell number 71. Cell number 71. Cell number
Yeah,
71 is value counts. Okay.
yeah. So
This is
here
what? This is count of, this is class? No, this is not class. Count of fam members.
sir, I feel like this is a discrete value, like something kind of
But what is
categorical.
this? We need to know this is what? What is this?
Yeah, so sir, data dictionary is not available at that
It's
place.
important that
We
we
have
should
to
read the
search
data
from.
dictionary. So the thing is that if 2 is number CNT fam members, anything which is low has it is yeah. So we need to understand this feature
Yeah,
actually.
that
Okay?
was that's the reason, sir, I connected to
Yeah.
you to understand the data dictionary,
No, so
nature
we
of the
don't
data.
okay, so data dictionary has to be there, okay? So I will try to grab the data dictionary, okay?
Yeah,
And try to see whether we have a data dictionary, okay?
and
This is
sir, we
count of
have.
family members, okay. Okay, okay. Awesome. Thanks, Shivraj. So this is what it is. This is count of family members. There are so many number of counts of family members, right? So do you need this in your feature? You don't, right?
Yeah,
Total number of counts on family members. Of course, right, people with less number of family members will be more. People
yeah.
with 15 members will be very less. So this
Yeah.
is expected.
Okay, okay,
This is expected, right? This is
okay,
expected, right? So you can actually keep it as it is.
okay.
Count of family members. So the what is our this our thing is that whether this is a loan prediction model. So I think this is an important attribute. Keep it as it is. When you scale it, right, automatically when you put your batch norm or scale, right, input scale and so on and so forth, this will anyway get adjusted. Do not do by 100. At least from when you give it to machine learning.
Okay,
When you are ready for model. Okay.
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 And sir, next question is like, can you go with the cell number 81?
81. Count of family members. Okay. So, okay. This is OBS counts total circle 30. Okay.
Hmm.
Anyone knows what is the data dictionary or what is the meaning of this column?
No.
No, so we have to know that. So that's an important thing. So what I'll do is like I'll also get myself acquainted.
Yeah,
Uh,
in the problem statement, sir, I think only data was given there, and the
hmm,
columns are not explained.
okay,
Right?
okay.
High range of columns, 122
I'll get
columns
the
are
data
there.
dictionary. But here, what is the problem? It's
Yeah.
again the
So
same thing, discrete value.
Yeah, so sir, suppose if we are going further, right, for the
Yeah.
model and all, right, so can we apply one hot encoder for these kind of things?
No, this is number, right? Why will you
Yeah.
use one hot encoder? This is not a categorical value, right?
Okay, okay, sir.
Is this a categorical value? One hot
No,
encoding
no.
is only for categorical value, isn't it?
Yeah, yeah, yeah.
So this is a number in numerical value. Please do standard scalar or Z code, at the input. And if you just add inside the network, if you add a batch knob, anyway, you're gonna add a batch knob, right? I think it's gonna be more than fine. This is not a categorical value. To me, it
Okay.
doesn't look like a categorical value.
Yeah. So, sir,
Okay.
there are few more columns I pasted, sir, in the chat box. These columns are having like missing values around 41,000 something. So I'm
Yeah.
not
So
able to
this is date
understand like.
columns, right? So this
Yeah.
is date column. What you can do is like,
Mm-hmm.
so this is all date, week, month, quarter, year, right? So maybe what you can do is like, this is categorical in nature, right?
So how to fill
So
like these missing values, sir? What criteria I can use here to fill these missing values?
yeah, I think date is gonna be difficult for you to think on that.
Yeah.
Okay, so this is, anyone has any suggestion on date? For now, as a first model, what you do is like you drop this number, 41,519 rows, okay? Anyway, you have 3 lakh columns, right? 3
Yeah.
lakh rows, right? 300,000 rows, right?
3.5 lakhs so
Yeah,
required to count.
3.5, 3, no, 3, I can see this, right? 307, 307,000 data points.
Yeah, yeah, yeah.
So I think
Like.
your first model should start with a small model, maybe
Mm-hmm.
10,000, 15,000. Ensure that your first epoch, you have a basic understanding. This is a binary classification, whether loan is given or not, right?
Yeah.
Is that correct?
Mm-hmm. Yes.
Yeah. So ensure that you at least in your first epoch reach 50% with a small data set. Then try to overfit that model. Okay. Ensure that your model architecture is pakka, perfect. When I'm
Okay.
saying model architecture, I am meaning this part of the code. Okay. I'm saying that this is the code. How many layers, total number of neurons is what I'm talking about. What you do,
Mm-hmm.
if I remember, we discussed this, right?
Yeah.
Once you build this thing, total number of layers, total number of
Mm-hmm.
neurons, your activation layer, your compile loss functions. Do these things and run one epoch on a small data set, maybe
Okay.
10,000, 20,000. Okay?
Okay.
And run one epoch and get your hypothesis right that your network, the core structure of network is found good. If that
Yeah.
is good, then add more data and slowly build that, start from there. That is a very important thing that one should do.
Yeah. So right
That
now,
is
sir,
a,
we can drop these columns like
for now, for as
by.
a first run, do drop it, then we'll come back. Okay, we can come
Okay.
back to it, right, and add it. We'll try to find out a way to add this thing back. Our objective is never to drop data.
Okay,
We
sir.
have a problem. The problem is that how do we impute, you know, date, and we feel that date is an important criteria to be given to this thing, right? Date is an important criteria we have to. You want to give date, right? You want to keep this feature to given to the model, right?
Yeah.
Yeah. So and anyway, this is a date is something of a category. How will you impute date in model? You have to do something or you have to remove it. You have to either keep these features or you have to remove these features, right?
Okay. Okay, sir.
Yeah.
So, sir,
But
most.
now I would suggest that rather than removing data, remove these 5 features, build your base model, bring the feature back. Okay.
Mm.
Think from this point of view, what is this amount required credit bureau date? Is this a reporting date? Or does this impact a person's loan history? I assume it is
Yeah.
not, right? So if you
Okay.
think from that point of view, it might not be required. Okay, and the logic is
Okay.
that as of now we are discussing without knowing the data dictionary in detail, is that it might not impact a person's credit
Yeah.
loan applicability. So as of now, the decision that one can be taken, given the
So,
assumption
sir,
is that.
I have taken, sir, one decision here. Like,
Mhm.
there are like 122 features, right, in the data set. So I dropped all those records where like
Don't
more
drop
than.
records, you can drop features. You're
Yeah.
dropping, yeah, okay.
Features, I dropped the features like which are more than like 31% of null values are there, right? So I dropped those features. So this is a valid decision or not?
But what you do is like mark it which are the features and then you can come back once your base architecture is good.
Yeah.
Slowly you can start adding. This is 122 features. We might need to do this. Okay? Fair
Okay.
enough.
And one problem statement is here, sir, as this is a category, classification problem, right? So, data is biased here as compared to target columns,
That
right?
is correct, right? So
Yeah.
number of
So,
people who get loans versus number of people who doesn't get loans is always skewed. No, if everybody get loans, we have a problem, right?
yeah, yeah, yeah. So, as per the problem statement, sir, I upsample the data by using
You can
resample
use Smoot. You can
scalar.
use Smoot or resampler, yeah. Random
Yeah.
sampler, yeah. Use
Okay.
Smoot. Smoot is a good library. It will be good for you to know Smoot as well.
Okay.
Smoot,
Okay.
you're imbalance, right? I am imblum, right? You can
Okay.
use
So
Smoot.
now, sir, now I used the sample from
Okay.
sklearn.util,
Yeah.
and I did that.
Okay, fine. I'm saying that for everyone's benefit, you can use Smoot as well. Okay?
Okay. Okay. Okay,
Smoot
sir.
is
I'll learn it.
emblem. You just have to do pip install. I'm just showing all of you. It's a fairly straightforward application. I can show you the code. This is how the code is. Fairly straightforward. Okay.
Thank you,
All
sir.
you have to do is Smoot, and then you can say that it will just fit. That's all it is, right?
Yeah. Thank you, sir. Most of the parts you have cleared.
Okay.
Main problem I was facing with the data pre-processing. I was not able to take the right decision here, but you
Okay.
cleared all my doubts. Okay. So I'm sure about the all problem state meant for the data pre-processing here, right?
Okay.
So thanks
Fine.
for all
Okay.
this.
Thank you. Okay.
And
I'm muting
from
you.
today,
I'm
I'm
muting you
going to
right.
do for
Yeah.
model building, deep learning
Please
kind
go
of
ahead.
thing,
Please go ahead. Please
right?
go ahead. Yeah.
Then
So
I'll
I'm
ask.
muting you now, Uttam. I will open Suchita. Suchita has raised her hand, so I'm you opening her.
Okay,
Thank
thank you,
you.
sir. Thank you.
Hey, hi. Please go ahead. Hello, Suchita, you want to speak? Hi. Is there any other questions? Okay. Now I saw that there is a tick mark that you have asked for, so I thought that you want to raise a question. Okay. Cool. Anyone else has a question? Okay, got it. Thanks. Thank you. Anyone else has a question, folks? Okay, so let's do one thing. Let's go back to our if we don't have anything, let's go back to our lesson plan. Okay, and so we'll do this, and we'll come back to this again and again. Don't worry. So what are we going to discuss? We will start with okay. Okay, so we've gone through yesterday. We've gone through LSTM, and before that we've looked at RNN. And can we use deep learning for normal machine learning problem also? Yeah, so of course, yeah. I mean, that's what we've been using, right? Remember the diabetes test case, the diabetes classification, whether you have whether a person has a diabetes or not, is actually a supervised learning problem. So all of these are machine learning problem. So neural network is just one way, another way. Whatever we know till now, it's just one another way, right? There is no, the problem has not changed, isn't it? If you think the problem has never changed, we are, people are just finding newer ways to attack the problem in a way that it is representational and it's very generic in nature. That's all it is, right? So this is house loan data. You must have done something similar, a classification, right, model, right? Deep learning code is easy compared to machine learning. In a way, it's because Keras has helped us. Keras, TensorFlow, PyTorch, Caffe2. There are many other frameworks. Keras has made it extremely easy. That if the framework is so extremely good that it is made very easy. However, from a different point of view, I shared it, yes, I shared it. No worries. I'll show you where I shared it. If you, so all of you should actually go to this place. I'm just showing you. I realize that maybe many of you don't are not there. If you go here, right, I've shared it on this week's Monday itself, right? I've shared in the community link. If you see that, for some reason it is showing multiple zip files. I've shared quite a bit of things. Even I've shared the CNN lesson, the forward pass, even the optimizer sheet as well. Okay. Please refer to this. I can. This is, I think this is copy. So this is where I've shared it. Okay. You can go to this post directly and download it. Okay. So, but Keras has done so. It's so, yeah, everything is community. Yeah. That is what it is. Most of the things are in community itself. Yeah. You can download any of these things from community. Okay. So the question is that, is it easy? Yeah, while coding it is, the APIs are really good, well done. Complicacy wise, that it hides a lot of complicacies, right? And no machine is, so, but this is a little bit more complicated. There are lots of elements because of the way it looks at it. My understanding, okay. That doesn't mean that machine learning is also pretty easy once you know it um, at that level, isn't it? Okay, so let's restart our learning process, and we will be doing assessment in today. So we have one practice, and you have one unassisted that you can do on your time, but we will look at one assisted practice, okay? That is sentiment analysis, okay? And we'll see that how LSTM can help us in doing sentiment analysis, okay? I'm sure from that there will be some more questions which we will actually attack it on maybe tomorrow or on Monday, all right? And I want to ask those questions, okay? So what we have looked yesterday is that we looked into LSTM. We looked into first RNN, and then we found out that RNN had this problem. What was the problem? RNN, a typical RNN cell, vanilla RNN cell had. Do we remember what was the problem RNN was having? There were two major problem. One problem that RNN had, which allowed creation of LSTM, right? Do we remember? Yeah. So its memory was what? It had memory. It had long-term memory also. But what was the problem? The problem was that it has not that big memory. Okay. The issue was that it was not having that big memory, and why it was not able to maintain the big memory. Long is just subjective to how long you want to be. Essentially, it was not able to handle too much recurrent. And why was it? Do we remember? That why part was important. Okay. Why was it? If our RNN cell had at its core was that the activation function was tanh, right? Do you think that tanh was causing the problem? Probably not, alright? Even if you change the tanh to ReLU, we would still have the short recurrent. The issue was in somewhere else, right? If you actually unwrap that back propagation of the function of an RNN network, you will realize that it causes a lot of vanishing gradient, right? If gradients vanish, at some point network will stop learning. There is nothing new to learn, right? That was one of the major problem with RNN. And what did LSTM did? LSTM took a different route altogether, right? It added 3 different networks for 3 different tasks to do a memory, and it ended up with having a cell like this, right? And what are the 3 parts of LSTM? Do we remember? What were the 3 parts of them? 3 things that three different networks of LSTM? A forget gate, a input gate, and no, cell is the whole thing. When you say cell is the whole thing. An output gate. There are 3 gates: a forget gate, input gate, output gate. They collectively build something. A for FT input, FT as a forget gate and our input gate they update the cell state, which is my long-term memory. And once my long-term memory is updated, that using that long-term memory and my output gate, I will generate my hidden state. Hidden state is nothing but a part of long-term memory, which is nothing, which is also called as cell state, which focuses on the current, the latest recurrent, the latest timestamp. Okay, so which is basically part of it. Very good. So this is pretty deep. In one cell has how many networks? Do you remember? How many networks we saw? We saw, if you remember, there are how many dense layers in one LSTM? 8, right? Forget gate has 1, input gate has 2. So forget gate has 2, input gate has 4, and then output gate has 2, right? So that's 8. That comprises of one LSTM. So this whole thing, this whole block is one LSTM unit, right? And all these are the three mathematical equations of forget gate, input gate, output gate. Again, the idea is simple, right? You take weights and biases and compute a long-term state and hidden state, right? So we've gone through this in our explainer sheet, but there is no harm in actually going through it one more time, right? So controls forget gate, right? So information, in fact this is better, right? If you have your previous hidden state coming in, remember your previous hidden state comes in from here and your previous cell state comes in from here. This function, okay, you will do this operation. This is element wise multiplication. This indicates element by multiplication. Do a plus. So this is my forget gate. Remember, okay. This is my input gate, and then the cell state comes in, right? The updated cell state is inputted, and this is my output gate. And this output gate's objective is to get my updated HT, which means my hidden state of the current layer. So this is what LSTM's information flow looks like. The only thing is that, so you can actually bunch them. The memory of one state is fed to another state, right? So, if you want to, and so this is one LSTM unit, just a different perspective. I somehow like this diagram. It shows you what is coming in, what operation is happening, who's giving us what, right? So when cell state goes in, this also goes here, right? This HT is nothing but this HT, right? So it's a continuous loop. And the way it's computed, it doesn't execute in loop. It happens concurrently, okay? Because of the power of, matrix multiplication, right? And it's just convenient. We did this yesterday, right? We will do this today. You will do this today, okay? And so this is not needed. This is the same code that you should not see. Okay. So what we'll do is we will go to the gated recurring read. This is one more style. This is one more improvement on top of recurrent cell or RNN cell, and we will quickly see what it does. Okay. Its objective is fairly simple, but however it is a little different than LSTM cell. It looks something like this. Okay, it has two gates. Okay, what its two gates are called as reset gate and an update gate. Okay, so the old state comes. Old state, in this case my hidden state, comes and gets computed. And my input comes. Now I think you can easily understand this image, right? Can you understand this image? Do you think you can understand this image? Right? Cross means element wise, this is dot product, right? This is going to be a dot product, right? And this is going to be a sigmoid activation function. This is also a sigmoid activation function. This part is output update gate. 10H is also a an activation function, right? And this is my hidden state coming out and getting an updated hidden state. And what is small t? Do we remember what is small t? What does a small t represents? It's an important way to think around it. This is the current timestamp. At what sequence which item in the sequence you are in? That is what is represented by a timestamp t. Okay, and at any point of time you will be at t. Your present time is t. Your past time is t minus 1, like that. Okay. It's easy to represent like that. Even in sequence we don't have any. This is not a time series, right? It's not only time series, but only thing is that time has a natural order. okay, which you cannot refute. Hence, you cannot reorder time, right? So hence, we generally use this in a notation of T wherever you want to order things. Okay, HT minus one will always come before HT, right? So that is what the general idea of it. Okay, if you actually see GRU has only two gates, determines the same thing it does, a little bit different than LSTM, and it has two gates. The updated ZT will be computed here. Again, two set of weights. One weight is computed for my input. Another weight will be computed for my hidden state. Pass it via a sigmoid operation. Okay, you will get an updated HT and this Z, and then you will have a reset gate which determines how much past information it needs to be forgotten. Right? Do you immediately see there is what is the immediate difference that you have from LSTM? Are you able to appreciate now that there is a difference between this and LSTM itself? And by this, just by having this limited information itself, can you guess which one will be better and why? So there are two gates. One is an update gates. Update gates, what it does is that it determines how much the past information, in this case HT minus one, needs to be passed along the future, and reset gate determines how much the past information needs to be forgotten, how much of HT I have to forget, right? After this, what it does is that it computes the current memory, okay, using this dot is nothing but a element wise multiplication, not dot product, okay, and you can also do the current state. So now just by hearing this, what do you think, which one will be better? GRU unit, get it recurrent unit, or an LSTM block? If you have been given a choice, which we always have, right? Which one will you use? Why? Why do you think you will use LSTM? How many networks are we talking about here? Sorry. I don't want to leak the answer. So which one will be? So LSTM is right. Generally, LSTM is right because it's anyway a deeper network, right? It has three gates, and it is trying to handle three parts of the problem independently. Here it feels right that all you are doing is update and reset, right? And you have gates for that. Also, it seems that long term part, the cell state, is not specified out carefully, right? Remember, so there is the LSTM had that advantage, feels like, from whatever we are seeing, isn't it? The cell state is not mentioned. Do we no? So that itself is a loss of some extra information, right? You still have two gates. Okay, it's a lesser information, which is true. These are the one of the reasons why generally LSTM is better. But if you have a smaller data set, okay, since LSTM is deep, and any deep network requires some amount of large data, isn't it? But if you have a small time series kind of a thing or a sequence, you can still work with GRU, and GRU can still beat LSTM then. But on an average, okay, you will see much more LSTM implementation, much more acceptance of LSTMs and its usage than GRU. Okay, so if you have to default your implementation, go with LSTM with ReLU. Okay, wherever you can. Okay, go with LSTM and with LSTMs. So this is what the LSTM versus this. It tracks a long-term dependency while mitigating the vanishing gradient, right? It has three gates, controls the exposure of memory content. It also does, GRU also does the same thing, but again it does same thing with two gates. Okay, and expose the entire cell state to the other. So BiLSTM is another version of LSTM. What is BiLSTM? The core block is LSTM. Do we remember what was BiLSTM does? Bidirectional LSTM, right? Bidirectional. When you say BLSTM, I'm assuming you are asking whether it is BiLSTM is or not. You look from both sides of it, not only from left to right. Check the sequence from right to left also, and if there is some value in learning from right to left also, right? From left to right and right to left, you can then join those two cell states and learn a lot more than that, right? So BiLSTM is better than LSTM, but you have to also understand it is deeper, right? It will take more time. one by LSTM block is two LSTM blocks, isn't it? So remember that as well, right? And also we can actually stack other LSTM on top of it. We have stacked LSTM, right? And you can have more deeper LSTM blocks and so on and so forth, right? So generally, if you have to implement an LSTM, please go with so if you have to implement a time series or a sequence kind of a thing, go with LSTM. So when we talk about time series itself, though there are a lot of people, you can use LSTM, but you have to ensure that you have enough amount of data. Okay, that part is on you. Stock prices, things that we saw has pretty much a good amount of data, fairly large amount of data. But most of the LSTM, most of the time series that you will might have may not actually end up having so much data. So in those cases, traditional machine learning or even your statistical based approaches might also just be fine. Right? Using a neural network um, has its own good as well as a little bit of heaviness, right? As well, right? Okay, good, great. What we discussed till now is an important aspect of modeling till now, which was recurrent, right? Recurrence. What was recurrence? Act of having something happening again and again, right? Chance of happening of something again and again, or the natural order of things. We have understood that it is not easy. We should not actually just simply add a column in our data set to say, just say, we can say that we'll add a feature called as order and we can say 1, 2, 3, 4. It's going to be very difficult because if we can do it for tabular data, right? But however, for language and all, or for other types of naturally occurring sequence data, it might be very very difficult to maintain a separate feature called as order. So what we did, we created a brand new network which was trying to get the recurrent out of it, right? The recurrence out of it as a feature. And that is what LSTM RNN GRU did. And it did it fairly well in such a way that it worked, right? Now there is another aspect of building intelligence which was very prevalent, and we see it again and again happening, is this idea of attention, right? This idea is also very important, and this is a feature. If you think that what are the important features that you really look at a data, attention comes out to be something which is very important. What is an attention? Attention is nothing but what is the most important features. If you have to talk to this, see this picture. This is a very famous picture, by the way. This picture, if you want to know about this picture, go to Wikipedia. So this is Lena image, CNN, right? So this is the Lena image, okay? This is a very, very famous standard test image used in the field of image processing since 1973, okay? So, and there's a reason why this image was used, and this image was used by, this researcher, okay, in his MIT's master thesis of image dithering. And this image was used in many fields and area. And recently, the model in the image, her name was Lena Forson. She appeared in that, right? I think last year somewhere. Sorry, 2015. Sorry, so sometime back in ICILP. ICILP is a very famous computer vision. Yes, she was asked to present there. Okay, so it was nice for her and for the community itself. But this is a very famous image. Please be aware of that. So now when you see this image, right? So we don't look at all parts of the image always, isn't it? We will look at very focused. So what is our focus right now when you look at it? Maybe you are looking at the eyes, okay, maybe you are looking at the hair, okay, maybe someone is looking at the background of it. That depends on the question that you are trying to ask. Now this kind of feature, it can be represented by something called as an attention. Okay, it's not a famous model. She was not a famous model, but yeah, I mean, this is a very famous picture in the world of image processing going on from 1973. Okay. But the point what I'm trying to say is that this idea that you have something called as attention is very common in human language. Right now, you might have a lot of distraction when you are watching, when you are attending this session, right? You might have a phone next to you, which is on a, maybe on a silent mode. You might have, background noises, but that doesn't seems to falter your attention on the session right now. I'm assuming, right? Because your mind may be taking a lot of noise. You are being still somehow been able to attend to this session and grab what you need, right? This particular feature is everywhere. The moment you see a feature, right? Do you see picture, right? Do you see all parts of the picture? No. Your mind will probably go and take bits and pieces of it consciously, subconsciously. We are focusing on what we need. That's a very valid way of saying that. What do we need? If the question is that, can you detect a hat? You should only, so moment I say that question, your eyes will only be looking at the hat. You will not be looking at anywhere else. Okay, so this is a hard feature, right? Think about it. This is actually a pretty interesting feature, that if you can, and this feature, this attention, this is called as attention. This particular feature vector or feature idea is called as attention. Now we model recurrence, and what we did is that we understood that there is this thing called as recurrence, and somehow we were able to extract that recurrence feature without hard coding the feature in our layer. We asked the model to learn them, nothing, learn from the data itself. Can we create a model which can learn this attention from the data itself? That is the question that we are trying to solve. And this is, I'm not sure where, I think in 2017, maybe before that, 2016, I remember, in Allen.ai has published a paper on attention with BiLSTM. No, I'm just discussing what is attention, okay, not model. So what is an attention? When I'm saying, right now you said that, can you brief me again? So that means you are listening. Maybe you couldn't understand. You're asking again. Even if lot of things happening in your surrounding, you are still trying to pay attention to what I am saying, right? It's Are you not audible? Sorry, am I not audible, guys? Can I get some yes or no's? Am I not audible? Okay, I am audible. Okay. Okay, so attention is that piece or that feature. Remember that attention is, it is not capturing specific bounding boxes. Specific bounding boxes is something that you have already gone to a solution of identifying that hat in the picture. Okay, I am not showing that, but how did you even go to the bounding box, right? Someone has to draw that, right? How did you even go there? Your eyes, when they are looking at the hat, you think carefully, it is not looking at anything else. Okay, so which part of the picture that you are looking for is a very important aspect, and we can call this feature as an attention. And the objective is that, is it possible for us to build or make this model, make a model in such a way which can extract this idea of attention as a feature from data. And this attention, if you read a book, think about it, if you are reading a book or a blog or whatever you want to read, do you read all the pages, all context, all at the same time? No, right? You read line by line, you make meaning, and then you go to line by line, right? Isn't it? So there also we see attention, right? Though you have a general context, you still will actually go line by line context, right? And so that is an important thing, right? So that not only narrows down your focus, while keeping a general knowledge up, right? So that's also how we read, right? So this idea of attention was there for some time, I guess, but can models be trained? Can a neural network be trained in such a way to capture this feature called as attention from images, from text, and from so on and so forth, right? So this has sort of revolutionized in some way. I'll show you a 2017 paper from Google, okay, from a bunch of people from Google, what they did. But let's get the idea of how it is. Okay, we will not be going to discussing too much on this, but let's get the idea and let's understand that this is something that has changing, and this is very fundamental to what we did. Okay, so attention can also be represented. Okay, it's a very it's well accepted that the typical and there is a framework called as encoder decoder network, and this is something that we will actually go through our next and last session, which is tomorrow. Maybe if we get time, we can start in today itself after the break. Is that this kind of network can be represented using this? The attention can also be used like this. Okay, if when you are doing machine translation, right? When you do a machine translation kind of a thing, when you're doing Hindi to whatever language you're comfortable with, do you do word by word translation? The actual translation, I'm talking about from a human language, not Google Translate. Right? Google Translate now has improved a lot, but I'm just saying we don't do word by word translation, right? We focus the core part of the problem and we translate that and fill the rest of the words around it, right? So that's also we will see that the translation is in natural language is so much of you know filled with attention itself, right? Even so this is so even so this itself has allowed us to increase a lot of things, and one of the things that we have seen is that even in our recurrent networks, right, how much recurrence that you will do, right? There's a limit to recurrence, right? I mean, you can say that how big your cell state will be, right? So there is always a limitation, right? Even if you are reading 1,000-page book, do you keep all your 1,000 pages on each and every word in your long-term memory? No, it's there somewhere, but you access your short-term memory more and more, right? Hence, your that memory is constrained over a long distance. So we would need some feature, some other thing, this attention, if we can somehow model this attention to bring back and to help us to improve our core recurrent network, right? So it's been seen again and again that if you use this feature and learn this feature called as attention, okay, and there's a lot of discussion and research has been gone through it. Okay, it's not a new thing, it is there for at least some time now. So what has been seen is that if you add this feature called as attention in LSTM itself, okay, there is a very high chance your LSTM network will improve a lot. Okay, so basically the idea is that even if you suppose instead of mapping your sentence A, B, C, which is a sequence, to your translated sequence alpha, beta, gamma, so you can ask your sentence to map C, B, A, okay, to alpha, beta, gamma, given the facts which says that, right, your distance between A to alpha is closer, B to beta is fairly close, and so on and so forth. And why it is close? Because of this attention. Okay, so this is just an intuition, guys. Okay, don't worry about the details, but the point is that so let's look at some examples of attention. I think you will now able to understand, right? If you the way an LSTM chooses, this is now we are now very clear on this part, right? LSTM chooses what to forget, what to insert, right, into the memory, and determines what inputs the network will attend to in the general phase. In either way, right? Even if for all these cases, one to many. Are we clear what is one to many, many to one? We've discussed it, right? One means we have one data which is outputting a sequence. This is a sequence to one, right? Your input is a sequence. This is sequence to sequence modeling, right? This is also sequence to sequence modeling, right? So this means that till now we were actually, our level was only one value, right? In many to many or sequence to sequence, your level is also a sequence. Sorry, your output is also a sequence. Okay, you need to give a lot of probability values, isn't it, to generate a sentence. So that is what it is. So in this case, it is always seen that if you actually so network, so it will help that to determine what the input, what this is, if your down part is input, what the network will attend to, right? This is very important. However, though you are trying to find out what it will forget and what to insert, can the network also find out what will this input attends to or paying attention to the output? Okay, what is this relationship of attention between these two, input and output? So that is a game. Okay, that is what it is trying to do. This is also if you actually see this, right, this is also a very nice way of representing, right? Mary was hungry. She didn't find any food any fine. So if you actually jumble the words, you will see that, when you decode and encode, there are some parts of it which is very, Mary was hungry, she didn't find any food. So there are some parts which are more important and has to be attended than the other parts of it, right? So this is all about food and being hungry about, right? When you decode word by word, right? Some parts will be more important, and what are those parts that can be given by this attention, this idea of attention? Okay. Um, Similar to images as well, right? If you actually have a cluttered translated MNIST input, you have a cluttered translated input, you can by attention, make them, uncluttered, or I would say you can translate them into an MNIST, proper MNIST input. Similar the way that LSTM chooses what to forget, and this is important. LSTM chooses what to forget and what to insert. You can allow a network to choose a path or choose a focus on your visual cortex, right? Suppose you are focusing on these nines. Okay, how do you know nine? You're really focusing, right? If you see how a kid draws, right, he or she will really focus on drawing this circle and then draw a long line, and then he will say nine. So that's attention, right? If he doesn't do this, then it will become six or five or something else, right? So now, what is your visual cortex? There is so much thing. 28 by 28 matrix, everything is empty. Your eye is only on nine. You are focusing only on nine. So ideally, if you do this, right, your search field also is narrowed, isn't it? And then you can actually have a you can choose a path to focus on the visual field. 8 is exactly here, not anywhere else. Everything else is just junk, right? This is something else, this is something else. I don't care about all the other cluttered images, right? For if there is a lot of handwritten notes, if there are a lot of dots, I can focus on where the most of my attention should go. The human beings have no problem whatsoever. You see, for us, it's just intuition, right? And we have been built to attend to things, important things, in a very easy manner, and that is what we are trying to give the power to the machine to do that. Okay, so it's clearly that, if you actually see this paper, LSTM will definitely, outperform if you actually ensure that if you add an attention layer to it. Okay, attention is actually a layer. Okay, if I am not wrong, let me just go and search in attention. Yeah, so you can see this, right? So you can see that it's actually a layer. Okay, and you can add it. There are different kinds of attention, I think, but attention is a layer that one can add it after understanding what it does. Okay, so this is what it basically is, right? If you consider an input or a sequence of images, okay, or a sequence for that matter, there will be an upper level representation which can choose where to look at, okay, by assigning a weight, right? So someone will tell you that someone has to tell the model at a higher level, maybe in the initial layers, that look here in this area, in this right corner, you should find the right things. Okay, don't look here and there. Okay, so that is what attention does. Okay, and again, it's going to be a bunch of multiplications and subtraction, but it does in a way which is pretty mind blowing. Okay, pretty good. But one thing is for sure, if you are using NLP, okay, or anything which has this feature of attention or the need for the feature of attention, use this layer, it will help you. NLP definitely use it. In fact, nowadays most of the thing is attention only, right? So this is one more way of looking at this. Look at this problem. What is NMT? NMT is neural machine translation. Okay, and this might be much easier for us to understand, right? If you so there was one more. One second, there was one more. So this is okay. So if you see that destiny is on what do you know? Can you understand what is this graph? This could be this is a very common popular graph, right? How can we generate this? You can, have you done that heat map, correlation graph of heat map? Heat map, yes, yeah. This is a typical heat map, yeah, right? So if you see that destination of the equipment means that Syria can no longer procure new chemical weapons, if this is what it is, and then its translation on the y-axis, which is on the down, right? You can find out based on this particular network's output, and you can correlate that some words are highly correlated and more important than others, right? And so basically it tells you that look at this part, okay? Maybe this means is not that important to translate. However, Syria has to be important, right? So map like this, a heat map like this can be generated from your attention layer, which can actually allow you to visualize things, okay? This is now standard NMT. Google Translate is I think it's the largest neural NMT system in the entire world, right? Attention is heavily used nowadays in everywhere. Image to text, caption generation, right? Is nothing but attention. This is a very important. See, in this image, you don't have any problem. You are trying to identify that this is a bird, right? But if I try to verbalize it, right, you will see bird on a water. You could have said something else, right? You could have said that I see a shadow of something here. You did not say that. 99% of people will say bird on a water. So most two important things is bird on a water, right? So if you see this first image, very small image, you can see that there is a sailboat and a person. Why? You could have said that there is a vast ocean, right? Black clouds and so on and so forth, right? So can we focus, or can you try to focus what is the most important part of and this is what it is. If you actually run this via some sort of an image attention layer, you see that the vision field will highlight this part, okay, based on what your person is standing on a beach with a surfboard, right? And if you can find out what is that your attention should be, in this case a bird catches his eye, then that you can translate into text via an LSTM layer, and then you can say that this particular image is most attentive to this particular word called as verb, right? Right? So this particular image is more attentive towards this particular word, okay, X and Y. And then you can teach your model like this. This is a very common thing that we don't realize that we do on a daily basis, on like second by second basis. But our objective of building attention networks is nothing but exactly this. This is one more way of looking at the neural attention model, okay? And you can see that the problem is, in this case, the problem is sentence summarization. What is sentence summarization? Do we understand this problem? Do we understand this problem of sentence summarization? Anyone that has done anything on sentence summarization? You have all done it actually, right? You must have done it when you were studying in the schools, right? Whatever language we have taken, doesn't matter. We will be asked to write a essay, or not essay, sorry, précis writing. Absolutely. Absolutely. Exactly. Someone will give you a big bunch of text from whatever language you are comfortable with and said, okay, make it short, because that short will go to newspaper, right? Remember? So that is exactly called as a problem of sentence summarization. So nowadays machines are used to do it, right? But how do you think you do it? You lose information. You have been given 100 line of text, but you have to do it, fit it in 50. Definitely you have to lose information, but you should not lose important information. It should still mean what it is. And how do you do it? You focus on highlights. Yep, absolutely right. This is exactly what I was supposed to say. You understand the highlights and then make a gist of it. That highlights, how will you focus on highlights? Highlights is nothing but attention. You need to focus on some parts more than the others, right? A Russian defense prime minister, Ivanov, called Sunday for creation of a joint front for combating global terrorism. I can focus my attention towards sorry folks. I can focus my attention towards Russian defense prime minister only. However, the objective is to summarize the whole thing, right? So Russia calls for a joint front against terrorism, right? So that's a nice way to put it. So here also you will see the output is an attention-based summarized model. So this feature, and I'm just saying feature because it becomes easier for me. I'm a machine learning guy. For me, everything needs to be feature, right? So however complicated understanding is that if I say that something is feature, then you can think that okay, now I have to model the feature. Either someone gives me the feature, but then if whoever gives me the feature has to be a human being or some systems. If they don't give it, then can I generate it? Because I also know neural network. Because I know that features can be extracted. Because I know that the birth of one of the key things about neural network is that they can generate features and we can generate features. When I say they, that we can generate features. So if I think that attention is a feature, if I thought that new recurrence was a feature, if I thought that ordering was a feature, time was a feature, some features might come from data, some features don't come. It is our objective to get it out. But suppose you do have this feature, then the whole game changes because your model improves a lot. It has been known that there's attention left, right, and center on human usages, right? So this is what typically if you have to formulate an NMT model, so neural net language models using a decoder encoder, we will look at that. Don't worry about it. And the formulation of the probabilistic estimates is nothing but this. Okay, and the encoder generally will look like this, but a decoder will look like something like this. So this, don't worry about this, but the point is that attention. Now let's look at one paper. Okay, this paper is not attention paper, but it says something else. You see that? What is the paper's name? Attention is all you need. It is one of the most popular paper now that it is. This came in 2017. Okay, till then, when the paper came, imagine that they must have been working on this for a couple of years or something like that, right? Maybe more. You never know. So till the paper came, right? This came in 2017, okay, and till then, NLP was pure play game of LSTM or complicated versions of LSTM, isn't it? You have like multiple LSTM layer looking at multiple things and so on and so forth and groove and really complicated stuff. But all neural net, we have already come to neural net and deep LSTMs, right? Now I'm just going to read a part of the abstract, and you will see, you will also realize that this paper is something that you can read now. I mean, you must have been, if you haven't read it, I would strongly suggest read this paper. Remove the maths part of it, but try to, if you want to understand attention, this gives you a good idea of what is attention. What it says is this: the dominant sequence models, I'm going to remove this transduction models, okay, part, and I can pick and choose what I want to remove, right, for you guys, right? Transaction is a very simple meaning, but the dominant sequence models, which is now till date, are complex or recurrent or convolution neural networks. Till that time, that includes the encoder-decoder architecture, which is what we've just now gone through. You encode or do feature representation, and then you decode it back. The best performing models was also the encoder-decoder through an attention mechanism. Right? This is what we've actually just now gone through it. Right? A typical sequence modeling via encoder-decoder. In this paper, we propose a simple network architecture called as the transformer. Okay, you all have heard of it. Now you know it, which is based solely on attention mechanism. Dispensing, this line is pretty earth defining, right? Dispensing the recurrence and convolutioning entirely. What they are seeing is that they have built a framework entirely using attentions, and they are calling it as transformer. There is not a single of recurrence nor any convolution operations at all. So they don't want to look at any part of images. They don't want recurrence also. So what they have done is that, so that is the attention is more, what has been said essentially is that attention is much more important than and overshadows if you can model it properly. Have you guys heard of this word called as transformer? So transformer is nowadays the most important model architecture. All this BERT, this is actually the start of BERT, by the way. Okay, BERT, and GPT-2, GPT-1, GPT-3, Bloom. Bloom has just launched yesterday, right, by Hugging Face. And so all of these are transformer models, right? Really, on end-to-end transformer models on NLP. And you'll also know that this is called as VIT, right? Visual transformers. Yeah. So you can see visual transformers, which is like till now we have just gone through this thing, right? What did we go through? Whatever. Guys, can you hear me? Yes, I just wanted to check whether I'm okay. So this is not a problem, at least. So visual transformer. So VIT is a transformer with architecture focused only, and this transformer, so by contrast, so it uses demonstrates a language. So a VIT is a visual transformer, does not use a CNN. Okay, so which is pretty weird. We know that CNNs does a lot of things. This is a very vision transformer started coming from 2020. This paper is from 2017. So you have now gone into the land of recents. Okay, ASTM was invented in 1997, if I'm not wrong. Okay, this attention based pure play attention based frameworks started coming from 2017. Okay, you can get a hand of it, you can build it, and if you see the introduction very clearly saying recurrent neural networks, both LSTM and gated recurring units have firmly established a set of machine approaches. However, however, numerous efforts has been done to continue to push the boundaries. We present that boundary is attention. So that is the reason I'm saying that it's in your benefit if you can spend some time on it. In this work, we propose the transformer a model architecture, removing a recurrence, instead relying entirely on the attention mechanism to draw the global dependencies between input and output. Very simple English, right? Anyone can read it. Strongly suggest read the abstract of this really awesome paper. You will be able to understand what an attention is, how important they are. And if you are really adventurous, so this is a typical attention architecture. It uses internally 12 layers or 13 layers. Okay. So this is again an input output or encoder decoder architecture. It has a lot of small details, like really like a lot of things are there, but as with anything new, you can unravel things and look slowly at each of them. That is, or take up a deep NLP course, you will be able to understand this. Right? So, but understand that whatever is happening right now is all mostly attention model. Google search is driven by BERT, which is nothing but a pretty large attention model. Many of the convolutions, visual transformers are also started coming up. They are saying that why do we need CNN? Attention is all you need. Okay. So that basically brings our end to RNN. Okay, and we've left at a point where which network is good for chatbot. Okay. So chatbot is what? It's a Q&A engine, right? A question answer engine. What is the problem statement that we are trying to solve in a question answer? Let's understand that. What's the problem statement that we are trying to solve in a question answer? Is it a classification problem or a regression problem or a text generation problem? How will you answer that? Based on that, I can say it's at a higher level. It's a text generation problem, but 99% of chatbots is not a text generation problem. It's actually a classification problem. If you classify something called as intent, okay, from that, not only you can also search what is the closest answer that is linked to a question. Okay, it's not pure play classification problem, but it's also classification plus question answer pairs, right? Which are close and not close, kind of a thing. You can use any of the BERT-based transformer models. Okay, they are already available in Hugging Face. Okay, you can not. Sorry, don't use DALI. Sorry, huggingface.co. Sorry. So go to models. Okay, so use the transformer-based architecture for text generation. For chatbot is a big problem. There's a lot of small things. Okay, if you are using building a chatbot from the ground up, there are a lot of small things that you have to do. Okay, at least 6-7 things. So So just question answering that, answering something itself is not enough. You have to do, if you are talking about classification or text classification, I think Hugging Face, any transformer based approach should just work by default well. But then you also have to worry about how do I find even if you get to the intent, how do I find the answer itself? That is important, right? That is also needed. Okay. But there are 6, 7 problems to solve a chatbot properly. Okay, all of them might have little things. Like suppose if you want to do a follow on, right? Even if you do classification on that, you suppose you ask a question like this, hey, what can you help me with? Can you help me with your account now? Can you tell me how can you help me? The person, human being on the other end replies, and then you ask a questions in the same context. How will you respond? So it's a bigger game, right? So, but yeah, most of this transformers architecture helps you to achieve a lot of NLP tasks, and many of those NLP independent NLP tasks like dialogue management, like intent classification, natural language NLU and understanding, text generation is NLG, natural language generation, which is nothing but text generation, right? If you see this, I'm trying to open Hugging Face. I don't know whether it is down or not. I think it is down. I wanted to show you guys. Okay, I think a lot of people are use this. They have released this Bloom, the news 176 billion parameter, which can solve things for 56 different languages. Okay, including the national language of India. Okay, so and you can do so. I think a lot of people are accessing it in some way. So if you actually go to models page on Hugging Face, you will see that there are a lot of um, problems and it's like really slow. So you can use so there are a lot of small problems that has to be done. There one more problem that you will have in chatbot. The reason I can talk about so much in chatbot because better part of my 7 years I have been building a chatbot platform from the ground up, so I understand it very well. Okay, that whole ecosystem of it. And one of the things that you can also do is this idea of embedding, and you should know this thing called as approximate nearest neighbor, right? There's a lot of small things we can discuss if you are interested. Okay, there's a bunch of things to go through it. Okay, if you're something that you're building from the scratch. Okay, so let's do one thing. Oh, awesome, very good, Shivraj. Yeah. Try, easiest way to do is if you want to do an easiest and extremely super easy way, we can discuss it as a small project. I can show you a extremely easiest way. It's not a classical machine learning approach, but it uses a model which which ensures that your meaning of the question versus the meaning of the answers are almost similar, and you can build a data set in such a way that they will be similar, and you can project them in some sort of space called as embedding space, and then you can search on that. Okay, it's a little trick. Yeah, I think. So the thing is that TF, IDF, vectorizer, and cosine similarity are very old school style. When I say that, it will not be able to help you. You should use. So you are using. Why are you using TF, IDF? You use this thing. Okay, Google Universal Sentence Encoder. Okay. So sentence. So this is a good embedding matrix. Okay, embedding system. And if you actually run this collab, so what it does is that it can vectorize this. So using TF-IDF, you get a one-odd encoded number, right? Instead of that, if you use this model, it gives like for elephant, it will give you a number like this, and this number is an awesome number. It can give a number for a word. It can also give you a number for a sentence. And once you have a number, this number is very representational across the whole world. Okay, they have built this model, this universal sentence encoder, with billions and billions of text. Okay, and you can actually go to this run in Colab and just see it. Okay, it's very simple to use. Like 3-4 lines of code, you will get an idea of what it is. Okay? So that's what I'm trying to say. Okay. Yeah, Hugging Face is down totally. Right. So now you can see this, right? So in text, right? If you go from tasks point of view, there are many sort of tasks, right? You have audio classification, question answering, summarization, zero shot classification, sentence similarity, token classification. All these things are various types of tasks. So not one model. Yeah, yeah, sure, no problem. So not one model is enough. Okay, many a times. So now this general active thing is going on. Build a really large language model or some model which should be able to do many tasks, right? And these are that's why we are seeing such big models. Okay. Um, we have about 5 more minutes before we um, wrap up for the first half of the session and we take a break. On the other side of the break, what we can do is like we can start on the autoencoder and we'll just get an intro of it. Okay, that's going to be mostly theory with small part of one lab. But what I really wanted to focus on is all your questions for next two sessions. Okay, maybe like from tomorrow's second half, like 24 hours from now, and Monday, we should ask like abundance of questions all around and get all our doubts clarified. And we should all be done with our projects if it's possible, because we are getting Saturday, Sunday, right? And you should have at least some sort of mechanism to do it, right? So if you can, okay. The assisted practice on 3, I think this is what you should be doing. Uh, it's this is fairly simple. What we can do is like let's do it after the break, okay? I want this to be done in a way which is representational correctly. And before that, before we break down to the before we take a break, I was thinking that what are the other things that we can discuss, okay? Over the last 1.5 sessions, right? Maybe Monday, these are all questions that we can. These are all this open-ended things. So there was a question that can we do a little bit of detail on backprop? I can do that, okay? And I want you to also discuss and at least aware of these concepts that they exist and they are impacting us big time now that you are neural network aware, right? Ideas of transfer learning, maybe we can discuss 5 minutes on top of it, because everywhere you have transfer learning only, right? We can also discuss if you have to create a brand new layer of a neural network in Keras, how will you do it, right? You might ask that why do you have to do it, but the thing is that every session you will have new networks. Yesterday it was RNN, LSTM, GRU, then suddenly we have attention now, right? So I think it's in our interest to know that what are the important tenets of creating a layer. You know it. It is just we can actually discuss if you are aware. This is something that we have talked about attention based, and I can show you some of the models. This we can touch base. I wanted to show you one demo on transformer actually. Very simple demo. One line of code done nowadays. Okay. We can discuss a little bit on the OpenCV package on computer vision. People who wants to go deep into vision. Okay. You can do very little without this particular OpenCV package. People who want to deep dive into NLP, right? Can we can discuss this. This is something that we can do a small demo. Okay. We can also go through what is vectorization, what is embedding, little small intros. Okay, so that you are aware of it, and then you can. What is this idea of large language model? Okay, why do you have to worry about it? Right? We can discuss GPU training. There was a question. I was just recollecting. Okay, who has what asked? So there was a question on GPU training. We can do that. Should you learn about NLP for chatbot development? Yeah, I mean learning is. I would never say no to learning. Right? If you can, definitely. Definitely you should learn. Yeah. The only thing is that what is your output? If your output is to only build chatbot development and you're done with it, no. Learn NLP from the basics so that it's used not only in chatbot development, in all development, right? It has to be a generic open-ended learning. Okay? Because whatever you will learn from chatbot development can be used on any other process, right? That's what I'm trying to say. You can say that, can you learn NLP? Yes, absolutely. Answer should be yes. Right? The target is up to you. Right. So I was thinking that these are the various things we can discuss in once we finish our lesson on a autoencoder, because autoencoder will mostly be theory, okay, and we should focus on little bit of practical. This all of this we can actually show a code, okay, maybe build a sample repository or library of code. I don't know whether it's possible for all of us or not, but at least we'll try, and that I can share with you folks, and that is something that you can refer, right? Is what I was thinking. This is also like GPU training. Someone was asking how to do GPU training in TensorFlow. Very simple. They have done TensorFlow by default support distributed training, right? We can discuss model and serving infrastructure. Big issue, right? ML ops, right? And huge area of. I've shown you something called as weights and biases, right? So those are things. These are the various topics that I have in mind. We can discuss. Okay. So let's do one thing. Let's take a break for 15 minutes. Okay, it's 9:30 in our my time zone, and we'll come back in 15 minutes time. Let me start the timer, and then let's resume our um, timer. 15. Oh my God. Right? And let's start our. What we'll do is like we'll do this thing. Okay, we will attempt the practice lab, and then we'll start our autoencoder. Okay. Thank you, folks. Let's see you in 15. Okay. Can you guys hear me? Shall we start? Shall we resume? Let me just put a earphone. So what are we gonna do now? So let's do Google Chrome. Let's go to our practice labs and let's attempt this. This problem of doing sentiment analysis. Okay. So sentiment analysis is what? You have, let's look at this problem statement. So what is sentiment analysis? Let's look at what is the problem that we are dealing with. You have lots of reviews and your objective is to try to find out whether it's whatever is the text is good or bad, right? It portrays something good about the content or it portrays something bad about the content, right? So of course this is an NLP data set. However, we will look at the dataset is actually inbuilt inside Keras dataset. Okay, there's a lot of things in Keras dataset. If you're interested, let's go to Keras dataset once. Okay, keras.io, and let's see. And this is datasets. Right? So this is Keras datasets. Okay, and there's a lot of things that we have. Right, we have Reuters. We will be focusing on this IMDb. I'm sharing my screen, right? Yeah, I'm sharing my screen. So we will be focusing on this IMDb movie review of sentiment analysis dataset, right? So this, you should know that it also has a Boston housing price regression dataset. Okay, and all these are though toy dataset, but actually gives you a flavor to build your own models quickly, test things out. So if you look at the data a little bit more, it's interesting to see that IMDb movie review sentiment classification dataset, right? What it is, this is a dataset of 25,000 movie reviews from IMDb, okay, labeled by sentiment positive or negative. So it's a binary classification, right? So there's only one positive or negative, right? The reviews, so these reviews are been pre-processed and each review is encoded as a list of word indexes. So for convenience, the word are indexed by the overall frequency in the dataset. So for the instance, the integer 3 encodes the third most frequent word in the data. What it means is that when we load this data, okay, you can actually reload the whole new data on your own, okay. So from here, but this is pretty large, okay. What it means essentially is that the part where they transform a text to number is already done to some degree, okay. We realize one thing, that each of the machine learnings only work with any machine learning algorithm will only work if the data is in numbers. We have to transform things into numbers, right? And that transformation is done in some way, okay. It's not the most optimum way, but it is done in some way, okay. And this is what it gives you, by the way, okay. So if you actually load the sentiment analysis IPYNB, I have renamed it. So if you go to your self-learning, you can download the solution from here, and I strongly suggest that you start running it down. So I've just renamed it because when I downloaded it, the name of the file was untitled, and Jupyter Notebook with untitled really takes me off. Okay, I don't like not to name the code like this. Okay, so that's the reason I just renamed it to the same file. I have renamed it to sentiment so that it is clear to me. So all I do is that this, okay, I'll import TensorFlow and just import the IMDb datasets from my data. I define something called as a vocabulary size, and so if you see this, right, so IMDb, what it does is that it does something very nice. Okay, it gives you IMDb and a load data kind of functionality, right? When you do this load data, it just loads the data. You can say that what is the num words? There is a num words, right? Right? Num words is nothing but what is the total vocabulary size? What's the dictionary of words that you are worried about? Okay, the full vocabulary size. So at the end of this load, if you do this right, it will, if you haven't loaded the zip file, it will download the tar zip file and unpack it and give you this xtrain, ytrain and xtest, ytest by default. Okay. And if you actually look at a very specific sample of xtrain, so this looks like this. Are you guys able to understand what is this? This is nothing but a sequence of words in some form. We don't know the actual words. They are already transformed or translated into a number or into an integer, which is nothing but it is representational of the fact that how frequently they occur, right? So the 3 indicates the third most frequent word in the data. So in this case, 1 indicates the first most important, what is that? Important, not important, the most frequent, which means how many number of times this particular word. This probably is the, right? The or words like this repeat a lot, right? Okay. And this is the level. Are we clear? Are we able to understand this? Is there any confusion? This is a part of an encoding that has already been done by Keras for us to take some advantage out of it. If this has not been there, then it would have been our headache, and this would have been had to be transformed into an NLP class to do that, translation of a text to a number via multiple steps. Okay, it's not going to be one step, right? But our objective is to get understanding of reviewing. No, review is a bunch of words. So these are all words. Each of the words represents. So these are all words. Okay, so there are so many words. So if you actually see the length of the, so let's see the length of this particular review xtrain 6. Okay, so this is a sentence, or we can say that review 6. The 6th review has 123 words. Okay, and each of those words are represented by this number. Okay, and these numbers essentially means that suppose it is the movie name. So the in this case is represented by 1, which why it is 1? Because it's the most frequent word. The is the most frequent word in the whole data. Okay? So that is what they are saying as per the Keras.io. You can see the 3 encodes the third most frequent word in data. So this is done because to allow us quick filtering operations. Consider only 10,000 top most common words and so on and so forth. So Keras has already given us this. If Keras has not given us this and given us the raw data, then this would have to be an NLP class, and we would have to spend time on cleaning the data, pruning the data, doing a lot of pre-processing on NLP data to come to this stage. Okay, we would still have to do this stage, but we have to do a lot of pruning. Okay, got it? Okay. So now, so that is the reason Keras gives you this ready-made data, so that our objective is to understand some concepts on top of it. Okay. Perfect. So now Keras also allows you to, IMDb.get word index. Now that you have this, you can also get a word index. Okay. So if you get a word index, it will tell you, so as I said, right? So you can apply the word index. So this is nothing but a big dictionary. For every such word, you can find out. So in this case, 1 is nothing but the, 2 is nothing but and, right? So this was the original review. You can see this. This 2, 1, 2, 3 like this probably. This was the original review. The and full involving too impressive, boring this as, and maybe what is happening is that this is in a this is in maybe ascending order or something. So essentially this is my review, this is my representational word. So if you actually see the ID word. So this is what it is, right? This line. Okay. So it is just an index is maintained separately. And this is a very classical NLP trick to maintain an index of words separately. People who have done TF vectorizer and all, or word index kind of thing, you will know this. Okay. Because we generally create a word index, and this in NLP, these are all my features, right? Words are my features, sentences are my features, and so on and so forth. I want it to be separately distributable, right? So that is what's the important thing. Okay. So let's try to find out what is my maximum review length. Apparently, the whole data set on XTrend and XTest, I have a max review length of 2697. Why I need to know this? I will come back to you. Why do I need to know this? This basically means, now, are we able to understand what are we going to do in this? If this is my one review, my objective is that from this review, I have to somehow build a supervised learning model, because historically I have been told that given this sequence of things, my target is 1. Similarly, there will be some sequence of things, target will be 0. So I have to build a supervised learning model using LSTM, so which should understand this sequence, and then it should be able to build that loss function, the classifier appropriately, right? Now the natural question is that if you have remembered, right, what will be the length of my sequence? Because my length of the sequence is very highly important, right? I have to actually tell the network that my length is this big, right? So I need to know what could be my maximum length, that is, of a review that is possible. It looks like there is some one review which is 2697, and I'm sure that this is a word length, that 2697 words in some review. Okay, and the minimum review was of 14 word length. Okay, so my thing is that there is a minimum review of 14, the maximum review of 2697. Okay, so this is an important thing. Let us try to understand one thing, is that what we'll do, we need to pad sequences. Why? Because this is variable length, right? So one of the things that with machine learning is that, can you have a variable features? Can you have a variable length features? Think about it. Can you have your x at one shape and y and x1 as one shape and x2 and one shape? No, right? It has to be generally one feature set, right? But in this case, it's a very classic NLP style thing, right? Is that, one review is 14, we can see that another review is 2697. So it is variable length, right? How will I ensure that all my features in my X are of same length, right? In one X, it is a 14 size array. In another, it is 2697 size array. I cannot just present this thing to a machine learning algorithm. It will go haywire. So what we generally do is, like, we choose a number in between. In this case, we have chosen a number of 500. If the review is within, so we will cut. If the review is more than 500, it will be cut. Okay, take the first most important 500 words. Okay, so we will say that from the start, take the first 500 words. Okay, if the review is not of 500 words, fill the rest of the words with zeros. In this case of minimum review length, what will happen is that first 14 are actual word, okay, and the rest will be filled with zeros. Okay, that is generally called as a pad sequences. Okay, this is a very common way of dealing things, and you can actually pad sequences both in front and there's two ways to pad it, two places you can pad. You can pad at the end of the word of the whole sentence, right? In this case, we are padding at the end. You can also pad in front. Okay, but be aware of the fact that there is always a chance for a machine to learn these zeros. Okay, with LSTM there was a chance. Okay, and you have to specify that don't learn. So most of the most of the words are going to be common for the review. Could be, but if you actually read it, so I'm not, so the and all, you can remove these things. If you are an NLP person, and doing a sentiment analysis, most of the time what you will do, you will remove these stop words. You can remove these stop words and keep the words that you feel it is important. So you can remove these simple common words, do it. But this is a neural network based system. We will not do such thing because we want the model to understand the meaning of it. And we know that in any languages, stop words also give you some meaning, right? If you remove the stop words, it's possible the meaning itself is changed. Then, then that might be a problem. So typically, nowadays nobody removes stop words in the hope of really meaning, getting the meaning out of the sentence. For us, it doesn't matter because it's a sequence, right? It's good that if you have more words and you'll learn the sequence, much better way, and you will be able to handle many types of scenarios, right? So we do padding, okay? We will pad X train and we will pad Y train. We have decided that we will only consider the first 500 such words, right? And this is how you do padding, okay? Keras has a pre-processing library. It's very mature enough, and you can use pad sequences. And if you now see this, take any one of those X train 0. So X train 0 was how much? 123, right? So this is pre-padding, okay? So I think this is pre-padding. It's putting 0 in front. Sorry, I remember. It's by default will put 0 in front because of that problem with LSTMs. It doesn't. No, it's not like. Do you like to lose data? I mean, whatever I'm saying, can I say without punctuations, without using articles, without using comma, only use what I mean, right? It will be difficult for you to even comprehend, right? Same idea. We would need these punctuations, we would need these stop words to make a meaning out of it, or else it's just bunch of proper nouns which basically has no meaning whatsoever on its own, right? So if you actually see the pad sequence data API, and so this is time understanding padding and masking. So this is what it is, right? What is this now? So let's see. So if you padding sequence data, right? If you see padding, so this is the pad sequence API, and so by default the padding is pre. Okay, yeah. So by default the padding is pre. Okay, if you want post padding, so this way it ensures that. So now what has happened is that, remember, our length of review was 123, right, for that 6th level. And now we said that our maximum review will be 500. So clearly, first 330, first 370 or 67 will be zeros, right? So this is what I did. First 367 are zeros, and the rest 123 are the real value. That's what it is. So now each of my X train is of 500 features each, right? How many features my X will have now? 500 features. And how many such X's are we talking about? What is the total X? So if you actually see, right, 25,000 something, right? 25,000. So total matrix I'm talking about is 25,000 samples. So this will actually give me 25,000 into 500 features. So there are 25,000 samples. Each sample has 500 features. So I have now successfully transformed each of my review into a number which has some sort of representational in nature. Okay. Whether these numbers are good, bad, and ugly, that's a different thing. It's definitely not appropriate for an NLP task. We need to be employing a embedding matrix to do that, and we will do that here. But we have these global models. I showed you, right? Google's Universal Sentence Encoder. You can pass on this whole sentence or a paragraph to Google Sentence Encoder. It will give you a number, and that number is generally 512 vector. Okay, dimension. Fair enough. But we have pretty big this thing. Okay. So let's build our model. Okay. Rest is very simple. Okay. We will add a sequential layer. Okay. and we'll add a new sort of layer called as embedding layer. Okay, let us look at what is this layer says. Okay. Anything new, it's always better if you actually see what it is. So embedding is a idea. It's a very, very important one. If you ask me, it's one of the most important idea where it tries to represent an object or a sample or something that is on real world as a number. If you want, if you can embed me, you can embed a picture, you can embed a sentence. Now let's look at Google's. And I wanted to show you guys. I do this for everyone. So let's see what this embedding means. Okay, these embeddings are one of the these embeddings are nothing but machine learning models. Okay, and they have been done using machine learning models, mostly unsupervised. But no, I don't think it's unsupervised. Um, yeah, I think this is done using autoencoder model, which we will take it, maybe after some time. But what it represents is a general knowledge understanding. Okay, that is what it represents, and this is a very important thing that it represents. So let us do one thing. Let us import our things. Okay, so this is the model that it takes. Okay, so I'm just loading the model. So this is a way. This is the code that Google only gave us, right? We are not doing anything separate. I'm just going to show you what it means. Okay, and I'm sure that you will be able to understand that. The reason is that a reason is not shown here. I know that you'll be able to understand because it is something related to a correlation matrix. Okay, let's give it 2-3 minutes before it comes. This is first time it will download. This model is about, I think, 1 GB or so. Okay, so let it take some time. Maybe what I'll do is, like, let's finish in the meantime. Let's finish our practice run. Okay, and I'll come back to, okay, it's done, right? So this particular model is embedded. If you want to see what is this model, you can go here and check the TensorFlow Hub's page. TensorFlow Hub is also a page. Okay, so what is a universal sentence encode? It encodes text into very high dimensional vectors that can be used for text classification, semantic similarity, clustering, or other NLP tasks. Essentially, this model will help me to transform this word, this sentence, this paragraph into some numbers. That's all it is. Okay, that's all it is, right? So if I run this text, right, let me run this thing. Okay, so basically, if I run this thing, I can see that elephant is translated into a 512 vector. Okay, and this particular sentence, I am a sentence for which I would like to get its embedding, is transformed into a 512 vector of this shape and these values. You might ask that, do they have any meaning? And that is where the beauty of an embedding model comes, right? And let's realize what is the beauty of an embedding model, right? So let's build this function. This function basically nothing but it just shows similarity. Now I have a bunch of messages. Okay, you tell me now. I have 3 messages. I like my phone. My phone is not good. Your cell phone looks good. Which of the two are same? Which is not same? I like my phone. Your cell phone is good, and my phone is not good. Among these three, we don't have a problem of saying that the second one is exactly the opposite of first two, right? Isn't it right? Is that correct? Right. So now from weather, will it snow tomorrow? Recently, a lot of hurricanes have hit US, and global warming is real, right? Last one, asking about it. How old are you? What is your age? If I ask you this question, these two are same, right? How old are you and what is your age are exactly the same question. But it is you and me understand. Machine has no clue. You ask the machine same thing, unless the person who was building chatbot. This is a question for you. How will you actually ensure that both of these questions will be answered in the same manner? It is a very, very, very difficult problem because making making machine understand meaning is a horrible problem, and that is where the game is, right? So now with this encoding, now what we did is that we have encoded the whole thing. Now let's encode all these individual sentences and run this function. This function, what does it do? It's very simple, okay? What it does is that it generates an embedding using that model. Okay, it's basically one line to get that embedding. And then generate a correlation. You know what is Pearson's correlation, right? It is nothing but the inner product of two features, right? You can also put all these things in a Panda data frame and do dot core. Dot core is nothing but this formula of np.inner. And then just do that heat map. You were talking about anode true, right? This is exactly the same thing. But we will simply plot it on a heat map. Let's see what happens. And then we'll talk about it, right? So what it happens is that you see this now. Okay, now it basically says that how similar are two sentences. I like my phone is of course same as I like my phone, right? Let's look at this. How old are you? And how old are you is here. In fact, why to declutter? Let's close all this thing and we can add our own sentences, right? So let's do this thing. So this is easier. So how old are you? And what is your age? See, it is saying it's very close. 0.8. It's really close, isn't it? Actually, what was you saying? We can run something called as anot equals to true, right? Let's just do that. Anot equals to true, right? I think that is anot equals to true. That will give us the number, which will be easy for us to quantify. So you can see it's 0.8. This particular model literally has told me that how old are you and what is your age is actually almost same. And this is possible only by this model called as embedding. The number that it generated, right? These kind of numbers are so wildly awesome, and this model was generated using by feeding trillions of text data over the internet, right? That is what the power of embedding is. You can get some meaning out of this, and this is what an embedding model does, okay? And transforming this text into numbers, 99% of cases you will use a model like this. There are many such models. Stanford has, this is called as embedding systems. You would have heard of it, GloVec, Word2Vec, fast text, right? There's a lot of models like this. This is one such model I just showed you from Google, but there are other models as well. But the point is that no, this is not, no, it's, did it depend on answer? No, you can see the code, right? The code is this. This is the code, that's it, embed, right? This is the code, nothing else is there. What is embed in the embed function? This is the embed function. You load the model from TensorHub and just call it, that's it, nothing else. Give the model input. If you can just do it like this itself. Okay, I just wanted to show you, okay? Just although yeah, so just go do code. So model, say, I love teaching machine learning. It's just a function. Huh? So model is where is model. So this is my where is my model? This is my model. So I can just call me this embed function. Let me just the same thing. What happened here? Oh, I have to give it an array, is it? I have to give it as an array. Okay, fair enough. So model, an array, right? An array, a model. That's what it is. Yeah, you can see this. Can you see something that I did? What I did, I actually made a mistake, right? Now let me do one thing. I actually made a mistake. So let me actually add this thing. Okay. I just wanted to show you guys how these models work, and then we can actually go to the lab. So you can see this, right? I'll make some mistake, leaning and learning. You can see this. Though I made a mistake, though I made a mistake, it is still able to find out from a meaning standpoint that they are very close. Okay? Though I made a mistake, if you have actually passed it via some sort of regex kind of a spell checker, they will say they are very far. Right? So this kind of tricks and techniques that you can do. What is scan change? Yeah, so okay, absolutely. That's a great one. Let's do that. You can see that it is going down, right? I hate teaching machine learning, right? You can put a threshold of 0.8 and then the meaning itself changes, right? Right? So the other thing is that this kind of things, if you want, I'll show you something else also. Is that you can using an embedding matrix, you can actually find out if man is to queen, then what a man is if a man is to woman, what will be king to what? The model will answer it's going to be a queen. Okay. So this is what is an embedding model is all about. Let's come back to our practice test cases. And in this case, we are not using an embedding model. However, we are using our own embedder, which has changed things into this kind of a number. Do we remember what was the number? It was let us print out that number just in case that we x underscore train. Okay. So this is our number. Is it a good number? Might not be. If we have used an embedding model, this number would have been much better, right? Because it's all of the game of the number. But you can use it. In this case, we are not using. If we have used this good number, you can. So your model will accuracy will go up. In this case, we'll put an embedding model, and then we'll put an LSTM 100 layer. Okay. Total number of units is LSTM 100. At the end, it's anyway a binary classification. So it doesn't matter. We can just give 1 and sigmoid is fine, right? Any one of the thing is fine. We don't have a problem with sigmoid here. So if we do a model summary, we can see that our embedding model itself has fairly large number of things to worry about, 16,000, right? And that itself dominates a lot because of our index is very high. And if you actually train our model, we have to do binary cross entropy here, right? We can do binary cross entropy. Okay, and just reduce the batch size to what is the 315. So that it will take some time, right, for us to go through. 315 is like what, almost half of 600. That's like 5 minutes each. So each epoch is taking 5 minutes. If you run this via a trainer, like a GPU kind of a trainer, it might actually reduce to a minute or so, maybe less. Okay. But it basically, if you just run these two epochs, this is our standard code of model fit. Definitely create this branch. You will see the accuracy probably is going up, loss is going down, and then you can do it, right? As simple as that. Our objective is to learn LSTM. I think LSTM is now probably understood, right? So you can actually build a fairly easy way in less than 20-30 lines, a model, which can do sentiment analysis from the scratch, isn't it? Okay. I think that is that understood, folks? Got it. Okay. Are you able to run all these things? Have you tried now? If you haven't, please try it. Maybe when you can. And there is also an unassisted practice project for you. Okay. And for this, let's discuss this as well. This is for LSTM. This is actually you have been given a news aggregator dataset. Okay, this news aggregator dataset I have shared the link in the community forum. It's a link from Kaggle. It's open source, so you can download it. Don't worry. Okay, and this is about a multi-class classification using LSTM. It's about it's a multi-class classification, right? I encourage you to actually. The objective is that given a news article, categorize into what sort of news it is, right? This is a good one, right? This is like It's a very common use case. People need it, right? Just given a type of email, where should you categorize? Gmail has now features to categorize, right? So this is a very common use case. Given lots and lots of emails, which department should I move to? Very, very difficult use cases. These banks and people with lots and lots of customer care support people, right, are facing, right? If you can actually build a classifier and push it to the right department, they'll pay you a lot of dollars for that, right? But the volume of emails and the volume of text is abundantly high there, right? Given a text, what will be the intent? A chatbot problem, right? So that is what we have to do, right? Okay, I think we have just come to the end of LSTM, and you know, there is also a practice and project. So this is the practice project. Solution is already given. So this is from a Tata Global .csv, right? So you can do this is stock market price forecasting. Whatever models you build, please don't deploy in your, at least please don't use it for your real trading if you are into such things. Okay? Just a disclaimer. Okay. Good. Any questions that we want to ask ourselves now before we move to a brand new topic? That's mostly theoretical in nature, so don't worry about it. And we will try to understand what an autoencoder does. Okay. From a theory standpoint, we have one practice test cases, but apart from that, I would like to all of you to start thinking about this. Okay. I realize that I have not. Just one second now. Just one second. This is general common terms. General common terms. General. Say put it. Okay. So I was thinking that. What happened? Okay. I was thinking that, I was talking before the call, right? Are the predictions for stock accurate? It will be. The only thing is that the number of, stock prediction is a very complicated problem, okay? So just thinking that if you take the feature of stock prices, historical stock prices is not enough. Can you guys tell me what it needs? What are the other types of features? Think about it from a data point of view. If you are someone who has been given this problem statement, do you think, no, it's not illegal to use? It is illegal to use this algo? No, I don't think it is illegal. You can use any algo for that matter. Okay? But the thing is that, think from a data point of view. Does the stock price depends on only the historical evidence of what has happened? What else it depends on? So the data set that you get is from Yahoo Finance, right? Yahoo Finance only captures the historical trend. But the stock price of anything, yeah, you don't have, do you have all the external, so how will you handle all the company's reputation? So do you have all the external feature, factors and current news, current market conditions? Is it there a recession or not? And so many things are going on, right? Is the weather is bad? What type of industry the company is in, right? Which government the company is in? So people who are really like big hedge funds, right? So that is they will have models or mathematical models which can analyze all these various things. It is not just only the historical price. So your features are really less. That is what I'm trying to say. Again, it just helps me if you put everything in a feature representation, okay? The moment you think that is my features enough, you might have an answer of yes or no. To me, the reason just by doing historical prices for stock is not sufficient, because it doesn't represent the actual problem statement. You need to have external features, many other features, which is highly data dependent. And you can say that, oh, no, 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 you can do feature engineering. No, 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 sorry. I have just learned, no, I have just learned neural network which can do feature extractions. I don't need any other features. The only historical features are also enough. But the point of the fact of the matter is that it can only take features which you from the feature that you have given. It cannot cook something up, right? So that is one of the things that you have to realize. As a data scientist, you start taking everything with a pinch of salt and try to analyze it as much as possible, right? Coming back, and before we start the autoencoder part, and I was thinking that in our rest of our refresher course, this is something that we can do. And if you all agree, then we can do it. We can start it from tomorrow after our finishing of our lesson, okay? And we can discuss this if you want, okay? We can do a back propagation, and we will just stop at the point of going into maths, or maybe going into deep into the differential equations. We can, but I think in the interest of everyone else, we will not. But I will leave you some tidbits and some places where you can do it. In fact, if you really are so interested, go and check. Yesterday I told you guys this guy's blog, right? Called as Kola, right? Kola. Yeah, so Kolas, right? Chrysolas, right? Chrysola has a very famous blog. And if you want, go and check this out. Calculation of backward propagation. Very, very popular blog. Not now, not of now, but what I will do is like the way I will do is like in such a way that you should be able to, no, we will do it in such a way, back propagation, that we should be able to really go to the understanding of it. And if suddenly some new network comes, we will not be, it will not be a shock for us. We can deconstruct it, just understand this equation, put that computational graph, right? And we can go to the point of doing differentiation, not do the actual differentiation, but we can understand it, right? So that much we can do. I think that's a good level for us to discuss. This is such an important topic, because this will give you a lot of boost, right? We will discuss a little bit of transfer learning. So what else? This attention network is fine. I think this is an overall game that if you guys really want anything else, okay, think about it. I will drop this note, okay? Let me actually drop it now itself, okay? Maybe one of you please copy it, or all of you please copy it, whether we should do these things or not, okay? Okay, I'm just putting it here. These are the various things we can discuss, 2 minutes, okay? I think that this will actually give you a better handle to continue in your journey with neural networks in multiple ways. And again, on Monday, we will be only discussing all your doubts. So again, I strongly urge, make a list of all your doubts, and let's discuss everything else, okay? And projects, please. Today was a good discussion. Let's do projects as well. Someone else also please actually start doing projects and share what are the various things that you have done. Thanks to Uttam today, he was able to show us what's happening inside that particular data set. Okay, that is important. Okay, folks, let's start on the final lesson of our course, okay, which is nothing but called as, so please can you guys copy this thing, okay, just copy this thing. There is no link, just copy it somewhere. I will also, maybe what I'll do is like I'll put it in the group itself, sorry, the community link itself, but maybe copy it and just think about it. Copy on your own and think about it, if this serves your purpose, or if you want to remove something and discuss something else. We will be spending 2 minutes, and maybe we will see some demos. Maybe we'll actually have a code ready for us to go ahead later and so forth. Okay, but if you want something else, we can run with that as well. Okay? Super. Okay. So let's start our final lesson. Okay, half an hour left for the day, and so we will discuss this idea or kind of a network on its own called as autoencoders. Okay, and what does it do? First of all, we were still in the landscape of unsupervised learning. Sorry, we were still in the landscape of supervised learning. Do you guys remember what was unsupervised learning? And though I'm sharing the screen, but do you guys remember what was unsupervised learning? Can you guys give me a algorithm which was for unsupervised learning? An algorithm which was for unsupervised learning. Okay, K means what else? One more. Give 2, 3 more. You have gone through it, right? One of the very popular, any kind of clustering algorithm. You said that K means is clustering algorithm. Any kinds of no supervised means no target variables. PCA, and there is an alternative to PCA also, right? PCA was when was PCA? PCA was long back, right? LDA is also unsupervised, yes, but it will need LDA is a target, right? LDA needs a target if I am not wrong. Okay, LSA might be unsupervised. Okay, but LDA might need a target, or it doesn't. Yeah, it doesn't need. Sorry, there's a TSNE, right? Yeah, LDA is supervised. Yeah, LDA needs a target actually. This thing, right? Your TSNE is a good alternative to PCA, right? Okay, the concept of PCA is linear. This is non-linear. Great. So, unsupervised, what does all of them do? They try to learn the structure of the data. We just came out of this awesome, you know, universal sentence encoder embedding, right? How do you think that this model was developed? This model, okay, you can go to the model page and read how it was developed actually. And how do you think this was developed? Right? This model is trained and supervised for grade length, right? How was it developed? Right? To generate a meaning of it, right? Yeah, I will put it. Yeah, I will put it out. No, this is something else. This is someone else, I guess. It's not mine. Okay, that's not mine. Okay, I will put it. Don't worry, folks. Okay. Let me just. So how do you? So this is one of the ways, right? So this is unsupervised learning techniques does what? It is basically is to learn structures, right? To learn representations, to correlation between input data where we do not have any level. So this is not the so for example, we can use clustering, compression, right? Feature engineering, representation, dimensional reduction, or generative models. All these things uses unsupervised learning techniques. Okay, one of which feature represent and representation learning. This is a very important paper. If you see the paper, let me see the paper. This was in representational learning in NLP, right? In deep learning. This paper was I'll get the paper, okay, and that was one of the. This is what it came around 2015, and which was the basis of this things, okay, of embedding systems, and that was one of the ways it changed the thing, right? And it actually was nothing but a unsupervised learning, right? As we discussed, PCA is highly unsupervised, right? It was invented like really like 122 years back, right? 121 years back. And it's a primarily a statistical approach of. Does anyone know how does PCA does it? Do we remember? No, no. So this is not the link, guys. One second. This is not the link. Let me give the right link so that we don't ask someone else something. Okay, let me just give you the right link, folks. So this is the right link. Okay, so this is the right link. Okay, so this is the right link. We can talk about this. Okay, and I now realize that I have actually put the text in the directly to LSM, not including you. So I just put it here. But this is what we discussed that we can put. Okay, so that's the one of the reason. Okay, okay. So PCA, how was it doing it? Someone said something and I overshoot it. Find gyre distribution with max variance. Yes, what it does is try to compute two things, right? What was it trying? Perfect, absolutely perfect. It was trying to create an eigenvector for each features, right? So that vector is nothing but a representation of that particular feature, right? Whatever the algorithm of PCA is, it's fine, but it was creating that vector, right? And you can actually use it for dimensional reduction. This is a classic unsupervised learning technique. From data, whatever you have in data, it's more than enough to draw some things out of it. By default, I think you should start using TSNE, but TSNE takes a little bit time, much time than PCA, because it is not a supervised. It's not a. It doesn't uses a line. Okay, it does not uses. It's not linear. It's non-linear. It has an activation function. Okay, and it uses a gradient descent to optimize some things. Okay, so that's what it is. You should use TSNE. TSNE was is recently developed, 2008, much recent than this, but it takes a lot of time. Okay, so what is autoencoder then? An autoencoder is another type of ANN, okay, which is used to learn this data encodings in a highly unsupervised manner, and this is a non-linear principal component of this is the data. This was the paper that introduced it using auto-assistive neural networks. Okay, this objective of autoencoder is to create or find data representation in a highly unsupervised manner. Okay, if you have to encode me or you and then transform into a number, why do we actually compute everything into number? Can anyone answer it? Why is this obsession with numbers? Apart from the fact that everything has to be 0 and 1, why do we actually need to be in numbers? Why do you think that all the features and all the data has to be in a number? Why do you think intuitively? We can do mathematical calculations on that. And if you are in an unsupervised world, what is the most basic fundamental of mathematical calculation? In unsupervised network, what was the basic of it? So we did this, right? Remember? How did we generate this correlation graph? It was doing what? It was doing a linear product, which is nothing but a distance computation, right? I try to find that how far is this one from this line, right? Now to compute a distance, we know that mathematics has lots of distance measures, right? It's very easy if you transform everything to 1, 1 is close to 2 by a degree of 1. But suppose if you transform 1 and then other value is 10, then there is a degree of 9 difference, right? So this idea can be easily applied, right? So this measure of distance and or which is used in a similarity idea of similarity can be applied left, right, and center. Autoencoder is one of those models which is nothing but a artificial neural network to use this. Okay. Can you explain again? My voice drops at that. Sorry. So autoencoders is a type of model which uses ANN, which is nothing but an artificial neural network, to learn these representations. You use PCA to learn the vector representation. You can use tsne, right? You have other sort of techniques, right? These are the very popular ones. You can also use autoencoders to understand this encoding, the data encodings, okay? And that is what it is, right? How does typically an autoencoder work? It has actually two fundamental parts of it, okay? First part is encoder, okay? It's called in this way because it encodes something, and the second part is decoder. Okay, so what it takes is that it will take an input, any input, it can be a language, text, and in this case it's an MNIST2, right? It takes an input, there is no Y here, remember, okay? Now, what it does is that it goes via this encoder model, right? And it will be a compressed representation. Can you guys tell me what could be this encoder model be? With whatever understanding that we have? If this is an image, what could this encoder model have to have this representation? Sorry, what is, yes, perfect. It can have on CNN, right? CNN produces numbers, right, which can represent a 2. CNN is nothing but feature representations, right? Perfect, right? And then if you have a CNN which represents a feature representation, right? And then you have a compressed form, what can a decoder then be? Decoded as to, so CNN loses things, right? CNN is a convolution operation. What will it do? It will lose things, right? But can you use a CNN, can you use, right? Can you use a CNN to use in a decoder? Sorry, my voice, yeah. So can you use a CNN in a decoder as well? CNN by default, the convolution operation by default does what? It actually compresses the image, right? And we have got some sort of representation, but can you actually build it back? Can you? We will see that. Even if you use stride, that means what? Okay, it's fine. Yes, perfect. I think you're right. We can, right? We can do something, but it might not be the exact representation, right? And why do we need this decoder? So we've encoded, if our objective is to get my compressed representation, why do we need this? We will see this, okay? Okay? But we understood, right? So what this is what is this is what an autoencoder does essentially at its basic tenets. There are two parts of network which is working towards on the data to explain it more. So it analyzes all the features on data in a very non-linear fashion. Okay, again, tsne is there, but tsne is not a neural network. Autoencoder is actually a neural network. Okay, so there's a huge difference between those two things, right? So, however, it also achieves PCA level capacity without even activation function, Okay, so first layer is like this, layer L2 and then layer L3. Okay, what does this mean? If you have x1, x hat is nothing but the output of that. This is decoding, this is encoding. First part is encoding, and the second part is decoding. And then if you have a decoder, what you can do technically is that, so let's go back to this original picture. How do you know this compressed representation is good or bad? How our objective is this compressed representation. We'll throw everything away, but we'll keep this compressed representation, right? That is what it is, right? How do we know that this will be good or bad? You can, in this case, you can generate this. My x will be my original input, and whatever my reconstructed input, we can do a difference of these two things and find out, right? If this two is really this two or not. Maybe there is some sort of loss. However, there will be some commonalities, right? How much common it is? Okay, there will be loss, no doubt about it, because you are definitely using CNN. It will be loss. It will be some sort of, it will be some gray, kind of grayish. Okay. However, how much loss it is have you start with 2, you encode it and bring it back. Is it 2 or something else? If it is something else, then your compressed representation is wrong. If it is 2 or close to 2, then your compressed representation is absolutely spot on. Okay, so that is how you can actually do it. Where all, sorry, where all do you think we use is, there's a lot of places autoencoders is used, right? We can use it to dimensionally reduce them. We have done that, right? In US, that universal sentence encoder case, if you see, we had, we had 500 features for each of the samples, right? Technically it's possible, technically we had 2000 something features, but for the sake of our practice netbook, we have reduced it to 500 features by just dropping everything else. We said that we'll only take top maximum 500 words, right? However, it was 2000, but my universal sentence encoder was giving me 512. So in a though it's not autoencoder, but in a way, it actually reduces your dimension. It helps in reduction of dimension. Reducing dimension will eventually make your network much lightweight, much better, isn't it? Right? It will also help you to denoise things. That is a very important thing, isn't it? Denoising is a very important thing. What is denoising? Anyone? Anyone understands what is denoising? Yeah, of course it will do anomaly detection, right? Anomaly detection is all about clustering itself, right? And if you see that your compressed representation does not conform with the common data set, then that itself is an anomaly, right? If you go back to our, you know, if you go back to our, so you give a lot of twos, lots and lots of twos, right? And all of them will have some or lot of numbers, 1 2 3 4 5. All of them will have some sort of compressed representation, and if all the compressed representation are good, they will all be huddled together, because generally 0 1 2 3 4 all represents a number, right? But suddenly you give an image of an A or an alphabet, that will be something totally of anomaly, right? That representation, that number might be totally different way of. So that is definitely sort of an anomaly detection. Okay, anomaly doesn't mean that bad. Anomaly means that whatever it was seeing, it is not suddenly seeing that something else, right? So that is what it is. If you, and it also do feature learning. Feature learning is something. So let's do one thing. I want to show you TensorBoard projector.tensorboard. This you have seen. I don't know whether I've shown it or not. I'll show you anyways, right? So if you see this, right, this is actually a vectored flow. Okay, so see this. This is a very common, word to vec. This is a very let's just load the MNIST image. This is something that we understand, right? Let's load MNIST image. So you will see that if you have done your numbering, as in like from the image to the number part correctly, then you will see all the nines are huddled together, right? So you will see that now I'm not able to show you. This, if you do tsne, it will take a lot of time. But what you will be able to see is that I'll give you a link and you can actually play around with it. That all the nines are huddled together, which means all the images which have 9 letter knows that they are common. And this is a classical, unsupervised learning. We know that this is 9, but there was no supervision towards it, right? So now, so let's see whether it can do it or not. I wanted to show it. I wanted to show it somewhere. This is no color map. Huh? Label 10 colors. Yeah. So now you can see this. Just 1 second now. So you can see this, all of the 10s together. This is what is this? This is all the 6 together, right? All the 6 are huddling together. This is nothing but clustering, right? And this is just on the MNIST dataset, by the way, guys. Nothing else, okay? Right? So making clusters. What I'm trying to say is that all the 6 are huddling together. Remember that. All the 1s are huddling together. So that if you have a good numbers, you can have representation like this. All the 9s are huddling together. Right? So that is what I'm trying to show you. Okay. Okay. Question is that denoising. So yeah, so you can denoise, right? If your image has lots of noise, you can smoothen things out. Denoising is nothing but, detecting what is noise is a different thing. But if you have noise, and we will see that autoencoder's output is actually denoising, the image will have a very smooth effect, because essentially you're going to lose information, right? The whole objective of doing down into and doing encoding to something small, CNN itself is loss, and then again putting it back will not be in exactly the same image. It will have some sort of denoising effect, right? If you have to build an autoencoder, if you do have to build an autoencoder, what do we have to do? You have actually four, 5 things you have to worry about. You need to actually put an encoder block. Its objective is to reduce the dimensions, input dimension, and compress the data. The whole act of compression itself is a loss, right? So bottleneck is nothing but that common area where we'll store the compressed representation, right? The compressed representation in its lowest possible form. You can decide what will be the vector size, 50, 500, 2000, whatever it is, right? But that is where it will store and then using that you should be able to construct to the original image or original data as same as possible. It will never ever be same, okay? Because the whole act of it itself is you're given the compressed representation, you have anyway killed it, you have anyway lost a lot of information, and then you try to decode it, and at the end you will try to measure the decoder's performance by finding how much reconstruction loss has happened, okay? Basically finding how big that 2 and this 2 was. If you are okay, you will see that if you have 2 and 2 this side with some noise gone or some pixels gone, you will be very happy with it, and you will have a very your objective of autoencoder is not the end part. His objective is that the bottleneck where you generate the compressed representation. Your objective is to get the representation out. This is also one way to consider that if you have to train something and learn, output always doesn't matter. The vector representation also matters. That is how also embeddings are trained, right? You will train with some fake objective, and after the objective is met, finding the fake objective is not an easy thing. Once you have that objective, throw the output layer, take the image representation, that is your vector representation. Okay. So we will stop it for today, okay? And let's spend last 10 minutes, whatever we have, with some sort of questions if you have. And we will continue this session tomorrow. It's going to be mostly theory, and with one practical, you will see that we will actually reduce the MNIST dataset with one thing. What is the end use of autoencoders? Okay. This is the end use of autoencoders, right? We've discussed it, right? You can use it for dimensional reduction. Do you agree that dimensional reduction is a very important aspect, right? We have very high dimensional data. You can use an autoencoder to reduce dimensional reduction, right? Denoising, like lot of image processing. You know that there's a new there's a new space telescope which is launched, right? And it has started giving data from long time, right? So there's a lot of effort has to be gone through denoising. Who does this kind of denoising? How will you do it? So autoencoders can help you to really do good denoising. Anomaly detection, spam, not spam. In your network, whether someone has logged in or not, some images are right. This kind of really high volume, extremely high volume anomaly detection, autoencoders are the way to go. It's very difficult for you to do because it supports neural network at its core. It's made of with neural network, which is meant with extreme data, right? It can handle data at n scale, and you need to do clustering or unsupervised learning technique at scale. No algorithm can actually handle it. Do you think your PCA will be able to handle it? Difficult. We just ran t-SNE. Remember, we just ran t-SNE on this project, right? TensorFlow. It took us for some 2-3 seconds to run some 60,000 images. You saw that, right? It was calculating finest, nearest, never, right? So it's slow.
on this itself and what will happen if it is production level anomaly detection. And one of the other very, very important aspect is that feature learning. We are interested to know that compressed representation so that that compressed representation can give us meaning, and with that meaning we can do those beautiful understand. We saw that one what that meaning can be, right? If you have a very good meaning of a word or a sentence or a paragraph, you can have you can represent meaning as a feature. So that is what is nothing but as feature learning, right? So that is you can do all these things using an auto encoding system. Okay. So and there are other types. So the auto encoders is little old architecture. Right now we have VAE called as variable auto encoders, if I am not wrong. Okay. It's VAE. Keras has an implementation, by the way. Yeah, variational autoencoder, and it is like it is the thing too, and you have a very nice implementation on MNIST as well, right? Um, so this is part of generative deep learning. You can generate stuff, right? This is nothing but think about it, right? You are actually generating things from a feature representation. Are you able to generate text? Can you generate image, right? If I say, right, we want to see this dolly keeps on coming, right? Let me show you, right? So if I say, though it's not exactly an auto, they are today learn. This is totally gone. I will show you something tomorrow. If you actually open this, you can say that you want an image of some random thing, and you will get the computer will draw an image. Though it's a poof kind of thing, but it gives you a flavor that saying something to generating an image, like literally generates, not searching, by the way. Huh? It will create the image vector. Okay, is something that is very common use cases nowadays, isn't it? So you can use VAE as a part of your generative deep learning. You can generate stuff. Till now we were extracting. Decoder is actually generating, right? Given a vector representation of something. That's deep, right? That's a lot of things that we can do, right? So that is what we have for autoencoders. You can use autoencoders for there are a lot of companies who does manual labeling, right? And then that gets feed onto the AI systems. So you can use systems which actually labels data. So this we can use all these things, autoencoders for that as well, right? You can find things out. There's a lot of use cases for autoencoders. Okay, there's part of those networks which little future kind of a thing, but I think it is all, at least these use cases what is listed here are all practical use cases right now. Okay, awesome. We are almost at the end of it, folks. Don't worry. I think we have a good journey. What we'll do is like, please go through the list of things that what I've put. Okay, this is from my head. Whatever I think that we should cover, at least touch base, even if we can't cover all of it. But if we can discuss, it will be really good. That's all I'm saying. Okay, and I'm open to actually add or delete things on this list. We will just be covering like one, 2 to 3 minutes kind of thing, or like some short time bound, and we will try to find out if there is some value in this or not. Okay, I think we have come to the end of the lesson. We have started lesson 8. Tomorrow, first half, we'll finish lesson 8, and from second half onwards, we will purely focus. So, second half definitely will focus on project. If you have more questions on the other projects, maybe you should start on the other projects as well, and maybe one of you can report back what is your first epoch. What was your first epoch accuracy? One epoch. Just run one epoch for accuracy, and that will itself tell a lot about what's your model architecture might look like. Okay, whether it is good, bad, or ugly. Think about it. Okay. Cool. I think we have come to an end of it. Is there any question that we want to take up now? We can take it, we can do it tomorrow, no problem. Okay. We can discuss. Encoder name, as in like our network architecture name. We can discuss these things, yeah. This like the whole architecture is encoder tech. Oh, encoder tech. Yeah, we will discuss this absolutely. We will go down actually. We will go down to a level of understanding how. So encoder is very simple. You did encoder itself, right? Remember, add CNN layer. It's an encoder. What you need to know is how do you decode. Encoder is very clear because encoder you have been doing taking inputs, putting lots of CNN, convolution operation is nothing but encoding. Taking the input, puts lots of LSTM and gives an output. If you remove the prediction part, don't what generally your last layer is softmax or sigmoid or some sort of function like that, right? Don't use that. Remove it. Keep your last layer, whatever is the output of the last layer is your cell representation, is your representation of the feature, isn't it? So that you have been doing anyways. How you now, from that compressed form, someone said that you pad a lot and then make the pyramid back, right? So from the pyramid you go to dust, and then from the dust you have to go to pyramid. The decoder is what maybe we have not done. Maybe we can take the decoder part. And anyway, we have to go through these things again. Okay, folks. I think we had a good run. Let's finish and touch base tomorrow, and let's talk about projects. Yes, please. And then I would love to also hear what are the other type of projects that you are doing. There are 3 projects actually. Maybe what you can do is that you can just check the data, download the data, load the data, and have this data understanding. Right? That will be a good place to start. Okay, folks, have a great night. If you are in this part of the world or wherever you are, have a great day ahead. Thank you very much. Thanks a lot. See you tomorrow.